observers have just detected something that shouldn't be possible, a chain of events that should not be appearing at the same time, and is so hard to explain that it feels unsettling. Right now, 7 comets are simultaneously plunging into the inner solar system and will in turn reach perihelion in the second half of 2025. Swan will brush close to Earth around October 21st, at a distance of about 1/4 of the Earth-Sun distance, roughly 37 million kilometers. Atlas K1 will skim near the Sun in early October. Lemon will reach perihelion on November 8th. The remaining visitors crowd into the same short time window. A calendar this packed has scarcely been recorded in the history of modern observation. But what truly makes this worrying is that the interstellar visitor 3 Ix's Atlas is also entering the stage right on cue, passing behind the Sun and then heading toward its October 29th perihelion, carrying an unusual composition and an orbit that never returns. The odds of 7 comets and an interstellar object gathering like this are extremely small, unless something is quietly coordinating them. What if this is not just a rare natural season, but the beginning of a more troubling scenario for satellites, navigation, and electrical infrastructure on Earth? Tonight, we'll explore every possibility, from statistics to the solar wind, and speculate about forces that may lie beyond our current understanding. Stay to the end to discover what's really behind the 2025 comet train. Subscribe to the channel and turn on notifications so you don't miss out. You and I will start from the ordinary to see the extraordinary more clearly. In most years, observatories observing calendars pass fairly quietly. 1 or 2 noteworthy bright comets, sometimes none at all. The rest are smudges visible only in long exposures taken by sky survey cameras. That's the steady breathing of the solar system we're used to. Then, in late 2025, that rhythm breaks like a strange chord. 7 comets at once dive into the inner regions, stacking orbital milestones atop one another within just a few months. For science, this is an anomalous cluster of events. For you and me, it's a rare chance to watch the sky's textbook turn its own pages before our eyes. When astronomers speak of a swarm, they aren't assigning it will or command. They're describing a crowd effect as seen from Earth, many dusty icy objects becoming noteworthy within a narrow time frame. I want you to picture a timeline stretching across decades. Each time a comet becomes bright enough, we mark a dot. In most years, the dots are sparse, like fine drizzle. But in 2025, the dots bunch into a bundle, as if someone had just poured a handful of glass marbles in one spot. At that point, the natural question is why? Why 7 instead of 2? Why the same season instead of scattered across years? Part of the answer lies in how we look. Today's automated sky surveys scan the heavens faster and deeper than ever. Systems like Pan-STARRS Catalina and spaceborne solar monitoring cameras have inadvertently become comet hunters. Thanks to them, we detect more objects. But one thing hasn't changed. Most discoveries are still faint, distant, and hard to see with the naked eye. The visitors bright enough for the public to look up and see for themselves are always few. So a year with as many as 7 prominent visitors jostling into the inner system remains a major exception, beyond the statistical habits of the modern era. NASA uses the word alert not to stoke fear, but to remind the scientific community that a giant natural laboratory is about to run right overhead. The Sun is cresting its activity cycle. Its wind and magnetic field will rub across those fragile ion tails, producing spectacular tail disconnection events we rarely get to observe in quick succession. Each comet is like a natural plasma probe, tracing invisible field lines with the electric blue light of ions. You and I can call this a field class in space physics, where concepts leave the chalkboard and appear like a thin wisp of smoke rising from a coal. Before we dive into names, I want you to agree with me on a few concepts. Perihelion is the moment a comet comes closest to the Sun. That's usually when it brightens, as subsurface ice meets heat, sublimates into gas, drags dust along, and creates the coma and 2 tails. Apparent brightness is measured in magnitudes. The smaller the number, the brighter. Under ideal dark skies, the human eye tops out around magnitude 6. And finally, the ecliptic plane, the imaginary plane in which the planets move. Many of this season's comets have orbits that cut across that plane, taking them through solar wind-rich space where observatories and probes can track the effects clearly. You might ask whether 7 objects arriving in the same season imply some coordinating hand. The honest answer is we must let the data speak. In some years, randomness produces dense clusters, just as, if you toss a fair coin long enough, you'll get runs of all heads. In astronomy, temporal clustering can emerge without any mysterious agent at all. In parallel, the scientific task is to test legitimate doubts. Do the orbits share traces of a common influence? Do the times they cross the ecliptic plane line up in a way that exceeds chance? If so, we'll need to think further about what physical mechanism could be responsible. The picture becomes even more interesting when an interstellar guest joins 6 inner system visitors. 3i Atlas doesn't belong to the Sun's family. It comes from another patch of sky, carrying chemistry unfamiliar to us. And after passing through it, will depart forever. On its own, it would be big news in any year. Sharing the sky with 6 inner system guests creates a rare comparison window. We can set matter from elsewhere, beside matter born in our own system, and watch them react to the same energy source in the same season. That's an experiment that normally takes many years, even decades, to piece together. On the emotional level, I know numbers can sometimes strip the sky of its poetry. So please keep both, the calm of data and the amazement of the eye. When you step onto your porch on a November morning and squint at a faint streak trailing across the stars, you're seeing not just a lump of ice and dust. You're seeing the sun's fingerprints on plasma. You're seeing ancient dust slivers bent by light pressure, like strands of thread. Beneath that beauty lie strict laws, and precisely because they're strict, we can forecast, we can agree to look up on the same night, in the same direction. There's one more thing worth saying early. This is not a story about an impact hazard. Orbital numbers show these visitors will pass by at safe distances of tens of millions of kilometers. What we need to prepare is not shelter, but time and a bit of patience. An ordinary pair of binoculars, a sky dark enough, a printed star map, or one on your phone, and a warm jacket if you live where the wind bites. You and I will use those simple tools to join a global observing campaign where amateurs' photos can add tiles to the mosaics built by major observatories. From here, our route will run on 2 parallel rails. One rail tells the big story of why this year's phenomenon is rare and why NASA's plasma modelers are debating the 2-way interaction between the solar wind and ion tails. The other rail takes you to meet each visitor in turn, from Pan Star's opening far out to Swan skimming close to Earth, from Atlas K, one sweeping near the sun, to Lemon promising appearances after sunset. And between the rails, 3i Atlas is like a car from another line merging in, giving us a long enough shared stretch to observe, compare, and pose new questions. To put it briefly, this section is only so you and I can agree on one thing. The anomaly is worth careful observation, not to chase sensational hypotheses, but to learn as much as possible from a season the sky has favored us with. Science grows not only from answers, but from questions asked in the right place at the right time. And perhaps there is no better time than a season when 7 comets arrive together, when we can hear the sky speak in many voices at once. To go on, you and I need a compact mental map. On that map, 3 layers stack up. The first is the calendar, where we place the perihelion dates and the times when visitors pass relatively near Earth. The second is geometry, where inclined orbits that cut across the ecliptic plane produce different viewing angles from Earth. The third is space weather, where the solar wind and magnetic field change with the activity cycle. When these 3 layers sync, the scene becomes far more vivid. I want you to imagine the statistical picture as a very long series of coin tosses. In a long enough series, there will be stretches of all heads in a row, even if the coin is perfectly fair. Astronomy is the same. A random distribution can produce dense clusters over short intervals. What makes 2025 stand out is that this cluster is not only dense, but diverse. We have distant, faint visitors, ones that skim very close to the sun, ones that cross the ecliptic at intriguing angles, and one that comes from outside the system. The combination of diversity and simultaneity makes this season a rare field class. On the methodological level, separating more detections from brighter objects is crucial. Thanks to automated surveys, we discover countless faint comets that would once have been missed. But comets bright enough for the public to see with the naked eye remain few. This is where selection bias often tricks us. In a rare year that concentrates many bright visitors, our brains automatically search for deeper causes, while part of the answer may simply be chance. Science's job is to test the hypotheses closest to nature first, and only give bold ideas a turn if the data force us to. Now, for a few concepts that will help you read this season's map. Perihelion is the closest point to the Sun on an orbit, and is usually when a comet is most active. Closest approach to Earth is a different milestone that depends on orbital geometry. It can come before or after perihelion. So don't be surprised if one comet flares at perihelion, yet is hard to observe because it lies near the Sun in the sky, while another sits in a favorable geometry, even if it isn't intrinsically strong. Position relative to the ecliptic matters too. Visitors passing near that plane tend to enter regions of denser solar wind, making the ion tail a living compass needle for the interplanetary magnetic field. The two tails make a perfect introductory lesson. The dust tail is wide and faint, bent by sunlight, and tells us about fine particles and grain sizes. The ion tail is narrow and blue, pulled straight away from the sun by the solar wind, and tells us about plasma and magnetic fields. When a solar storm arrives, the ion tail can be severed. The scene looks as if some invisible scissors snipped it. The old segment drifts off while a new tail sprouts at once in the direction of the newly shifted solar wind. If you see a thin blue ribbon suddenly break and reconnect, it isn't magic, it's plasma physics performing live. Because the sun is in a lively phase, you and I may witness such events more often than usual. Modeling teams at space agencies debate the degree of two-way impact. One side stresses that comets are mostly passive tracers sketching the solar wind. The other asks whether the plasma and dust clouds from many visitors at once might seed small perturbations in the magnetic flow. Whichever side is more right, one certainty is that every recorded disconnection will be a valuable data point in understanding how the solar system operates under harsh space weather. You may be wondering whether we'll see anything with the naked eye. The answer is yes, if the sky is dark enough and you pick the right times. A few visitors promise to reach easy binocular range, and some may even touch the naked eye threshold. But comet brightness forecasts are always humble. A thick dust mantle can insulate and suppress activity. A sudden fissure can expose fresh ice and cause a flare. So rather than making absolute appointments, it's better to follow updated light curves and be flexible for surprises. I want to spend a few minutes on practical guidance, because this is how you participate rather than just listen. Choose a site with a clear horizon in the direction of view. Avoid streetlights, dim your phone, or use dark mode to preserve night vision. A 7x50 or 10x50 binocular is plenty. Print a star map or save the comet's nightly track in your local time. Give your eyes at least 20 minutes to adjust to the dark. You'll see much more. If the target lies near the sun, do not observe while the sun is above the horizon. Eye safety always matters more than any photo. Another channel you can use is the coronagraph cameras on satellites. They record the sun's outer surroundings, where close passing visitors show up like tiny bright motes crawling across a fixed star field. This is a terrific window when a comet is so near the sun that ground-based viewing is difficult. Combine the two and you'll follow the story more completely. Watch the space cameras by day, then step outside to the real sky by night. If you enjoy contributing to citizen science, every observation has value. A simple log with date and time, location, sky conditions, tools used, impressions of brightness, and tail length is already a brick in the wall. Photos can add structural detail to the tail, especially if you keep raw data and precise timestamps. Set side by side from hundreds of people, those data bits build a real-time picture that major observatories can't fully cover. As for me, what excites me most isn't a spectacular outburst though who doesn't love a surprise. I hope to see one clear disconnection right as a solar storm rolls in, so I compare that sight with simultaneous solar, wind and magnetic field graphs. You may choose differently. Some just want to glimpse a faint streak after sunset. A reminder that ancient material still returns to tell stories whenever it gets the chance. Whatever the goal, we're on the same train. Before moving to the specific guest list, I want to stress a mindset. We don't have to choose between awe and discipline. You and I can hold both. We can look up and take notes. We can allow ourselves bold questions and be ready to set them down if the data won't hold them up. That's how science matures. And the sky is always wide enough for both heart and reason. In the next section, we'll start the roll call from the quiet outer approach to the harsh glare near the sun. Each visitor carries its own rhythm, and together they form the symphony of a rare season. You and I will listen to each part, and then to the whole. You and I will begin the roll call with two very different rhythms. One slow, distant, like the background drumbeat at the edge of an orchestra. That's Pan-STARRS, the opening guest, but standing far out where sunlight is only enough to stir a faint haze. And one quick, close, skimming fast, giving us the urgency of rush hour traffic. That's Swan, the streak of light with the chance to pass nearest to Earth of the entire season. This pair, if observed together, will teach you and me almost everything we need to know about how to read a comet in the field. Pan-STARRS is first of all a story about patience. When it reaches perihelion farther out than Mars's orbit, the sun's energy is so weak that surface activity is mostly very slow sublimation of volatile ices. This makes Pan-STARRS a target for large telescopes and long exposures, not for the naked eye or standard binoculars. But don't dismiss it. Distant comets like this are windows into the opening chapter of a physical process, where the dust mantle is still fairly intact and the underlying ice is just beginning to vent gas. When researchers track the light curve at this stage, they aren't only measuring brightness, they're inferring the composition and structure of the crust, the level of fracturing, and the efficiency of gas escape at low temperatures. In other words, Pan-STARRS is a beginner's course in ancient matter. It tells you how a comet slowly wakes from its long, icy sleep. On the geometric level, Pan-STARRS reminds us of an important difference. Perihelion does not equal visibility. If the comet's projection onto the sky lies near the sun, then even if activity is strong, observing from Earth is still difficult. On deeply dark rural nights, a small telescope may be enough to pick out a faint smear if you know the exact location, but patience is the key. I often suggest starting with guiding photos, matching star fields, and not being discouraged if the first night shows only grainy noise. Training your eye to recognize subtle changes in the star background means you're practicing a classic observing skill that generations of comet hunters honed before the digital camera era. Swan, on the other hand, brings a completely different rhythm. This is the guest with favorable geometry for Earth throughout the season, and more importantly, one that may sweep close enough for binoculars to be the ideal tool. The distinctive feature of Swan lies in its angular speed and phase angle. When a comet sweeps close to the Earth-Sun line, light scattering off the dust can be enhanced by forward scattering, making the head and tail look unusually prominent during a narrow window near dawn. You can picture this the way dust glitters when you look sideways through a sunbeam falling across a window. Not every night shows it, but when the conditions align, you'll be surprised at the apparent length of the tail and the sharpness of its structure. I like how Swan invites you and me to leave the house earlier than usual. Across most US states, the hours before sunrise are the best viewing time. When the target has climbed high enough to escape the thick atmosphere near the horizon, but the sun hasn't yet brightened the sky. Choose a spot with a clear view to the southeast, avoiding direct lights. With 10 times 50 binoculars, sweep slowly, letting your eyes lead rather than trying to pin a coordinate. A comet does not appear as a sharp point like a star, but as a misty streak fading from head to tail. A small trick is to use averted vision looking slightly aside, to let the more light-sensitive part of the retina catch faint details better than direct gaze. Swan is also a live lesson about the solar wind. Its ion tail, thin and pale blue, always points straight away from the sun, independent of the comet's direction of travel. This makes many new observers think the tail doesn't match the path. In reality, it's the mark of plasma. The solar wind is like an invisible river, and the ion tail is a thin algae strand stretched out by the current. When a solar storm arrives, this tail can be cut. If you follow space weather reports or community updates, you may catch the moment of disconnection. Images often show a gap near the head, with a detached strip drifting away, then a new, thinner tail sprouting in the direction of the shifted wind. For people on the ground, that's a rare live performance of plasma physics. There's a common misunderstanding I want you and me to clear up right away. A comet approaching Earth within tenths of an astronomical unit may sound dangerous, but in the language of space, it's still safe. The point of interest is not collision, but the observing opportunity. Agencies like NASA track such trajectories closely, partly for flight safety, partly for science. With Swan, closeness is a ticket for dozens of observatories to capture images, spectra, and track changes by the hour and by the day. It's campaigns like these that help us better understand the link between solar storms and tail morphology. Between Pan-STARRS and Swan, you'll see a continuous spectrum from low to high. Pan-STARRS teaches us the slow patience of ancient matter far out. Swan shows us the dynamism of dust and plasma up close. If you're planning practically, I suggest splitting your time between the two rhythms. Spend a few nights under dark skies testing yourself with a faint target, like Pan-STARRS, using short exposures and binoculars. Spend a few dawns on Swan, practicing reading tail structure, estimating apparent length, and noting changes across consecutive sessions. Those notes, set against solar activity graphs for the same days, will give you a new aesthetic sense of how science and beauty intertwine. One small but educational detail is angular speed. When Swan is near, it moves relatively fast against the star background. If you take a series of photos a few minutes apart, you'll see the comet's head drift slightly compared to the fixed stars. For beginners, that's an astonishing moment. The sky, usually felt as static, suddenly appears as a stage with motion measurable on a wristwatch scale. That feeling has turned many passive skywatchers into active observers. On an emotional note, I'll confess something. I love the quiet moments with tough targets like Pan-STARRS, when a faint blur finally shows itself after tens of minutes of searching, like finding an ancient coin in the grass. But I also can't resist the pull of a bold, bright sweep like Swan, where you can invite a few friends, hand them binoculars, and share a collective wow as the tail stretches across the dawn. Those two experiences don't cancel each other out. They complement each other, opening your heart to more shades of wonder the sky offers. Leaving this duo for the next visitors, you and I now hold two keys. The key to patience for distant, faint objects. The key to initiative for quick, close moments. Added to that are a few fundamental physics concepts about dust tails, ion tails, phase angles, and space weather. From here, we're ready to move into the furnace, where steep orbits, scorching perihelia, and one interstellar guest will pose new questions. From Pan-STARRS' slow rhythm and Swan's near sweep, you and I step into a more dramatic region where harsh sunlight is both spotlight and curtain, making ground-based observation difficult. Here stand two interesting characters. Stereo, a comet that truly co-stars with the sun-observing spacecraft, is often lost in glare when seen from Earth. And Atlas K1, the daredevil diving into a tight orbit so close to the sun that every passing hour is a test of ice and dust. These two guests teach us how to observe when the daytime sky dominates, and how to read activity signals that change quickly around perihelion. Stereo is, first of all, a story of hidden geometry. Its orbit dips below the ecliptic, putting it near the sun in our sky at perihelion. That means that even if it's highly active, its ion and dust tails are swallowed by daylight glare if you try from the ground. So how do we see it? The answer is in the coronagraph cameras of observatories like SOHO and the Stereo spacecraft. These cameras use a disk to block the sun's bright face, letting them record the corona where comets appear as tiny bright motes crawling across the starfield. There you can see the ion tail pulled straight outward by the solar wind, sometimes as thin as a pen stroke, sometimes trembling with magnetic ripples. What's fascinating about stereo is that it forces us to observe by the rhythm of space, not the rhythm of traditional night skies. By day, you can open near real-time images from coronagraphs to watch their motion. By night, you can take notes and cross-check with solar wind data published publicly. When a coronal mass ejection leaves the sun, it takes time for the shockwave to reach the comet's position. If at that moment Stereo's ion tail shows a break, you and I are witnessing a live plasma lesson. The timing alignment between field data and tail disconnection imagery is the kind of elegant evidence rare in observational astronomy. Because of its difficult position from Earth, stereo reminds us of a key safety rule. Never try binoculars or telescopes near the sun while it's above the horizon or just barely set. The risk to the eyes is irreversible. For targets like stereo, the best path is to trust spaceborne cameras and wait for rare windows when it pulls far enough from glare to appear in a darkening sky after sunset or before dawn. Even then, most of its best moments will be seen on screens, and that's perfectly fine. Modern science is the partnership of human eyes and instruments placed where we cannot stand. From this blazing stage, Atlas Swan steps forward like a stunt performer. With perihelion closer than Mercury's average orbit, the solar radiation it receives skyrockets. As heat blasts into the crust, ice sublimates furiously, dust is dragged along, and localized jets may erupt from directional fissures. For you and me, this translates into two experiences. First, the light curve may flare rapidly, then fall, reflecting bursts of fresh ice exposure. Second, the coma and tail shape may change daily, even hourly, as jets rotate with the nucleus's spin, altering reflected light and gas output. This is where a useful practice concept appears. The AFR parameter, a simplified measure of dust productivity, helps you and me compare activity across nights without distance confusing the picture. Most amateurs don't calculate AFP, but we can learn to read it in science reports to know whether a brightness surge comes from true dust output or just favorable geometry. If Atlas K1 shows alpha rising with brightness, we're seeing a real source change. If brightness rises but alpha holds steady, it may just be phase angle or scattering effects. Atlas K1 is also a lesson in non-gravitational forces. When a comet vents strongly from one side, it receives a small but cumulative push. Astronomers must add non-gravitational parameters to orbital models to match observed positions over time. For you, this explains why predicted paths are sometimes tweaked around perihelion. For me, it's a vivid portrait of a spinning nucleus breathing under thermal stress. If, during a campaign, you record a small deviation from prediction, don't assume you're wrong. You may have just brushed against the trace of inner activity. On the ground, Atlas K1 is usually tough because it lies close to the sun in the sky. Got near perihelion, the best windows are twilight, when the elongation from the sun is just enough to pull it from the glare. A clear horizon, dry air, and averted vision help. Standard binoculars may reveal the fuzzy head and a short tail if brightness meets expectations. Short exposures with a tripod-mounted camera, moderate focal length, and not too high ISO can capture longer tails than the eye perceives. Don't be surprised if Atlas K1 looks a bit different each night. That's the nature of a hot comet. Amid all this technical detail, I want to keep a thread of feeling. There's a unique beauty in targets near the sun. The sky is still pale blue, one evening star is just visible, and you notice a faint, breath-like streak at the day's edge. It feels like stumbling on a secret in a crowded street. Everything is normal, yet a small detail tells you the solar system is staging its own play, regardless of our work schedules. With Stereo and Atlas K1, that secrecy is even sharper. Most of the time, they act within the glare, and you only catch them when the curtain shifts aside. I also want you and me to be frank about the risk of expectation. Predicting comet brightness is hard. A thick dust shell may insulate too well, making Atlas K one less spectacular than hoped. Conversely, a deep crack may trigger an outburst big enough to set social media alight overnight. The right approach is to follow updates, stay flexible, and enjoy the learning curve rather than hang hopes on a specific magnitude. With that mindset, every observing night has value, even when the target falls short. You've learned to read the sky in one of its hardest regions. Finally, Stereo and Atlas K1 set up a natural transition to the next act. Once you've grown used to watching comets through coronagraphs, reading tail disconnections, and patiently hunting near sun targets, you're ready for the visitor drawing everyone's attention. An object not belonging to our family, on an escape trajectory, carrying unusual chemistry. 3I Atlas waits just around the corner, where we'll talk about its interstellar origin, its gas composition unlike most inner-system comets, and the meaning of placing two chemical worlds side by side in the same season. It's time for you and me to devote a section to the figure whose very name makes the astronomy community pause. 3I Atlas does not come from the cold reservoirs of the solar system. It carries the passport of another star, passing through our skies only to leave forever. That's why every minute of observation is a minute of dialogue with a distant place we have never reached. Before 3I Atlas, we had met two interstellar visitors. Oumuamua in 2017, mysterious for its lack of a clear tail and odd brightness behavior, sparking many hypotheses before the data settled them down. Borisov in 2019, clearly a comet in the classic sense, with a tail and surface activity easier to understand. 3I Atlas stands between those two stories. It resembles Borisov in that it is venting gas, but differs in composition and orbital geometry, giving us a new angle on how material from another star system reacts under our sun. The first thing to note is the escape geometry of 3I Atlas. It follows a hyperbolic orbit, meaning its eccentricity is greater than 1. Simply put, it's arriving too fast for the sun to hold. After swinging through perihelion, it will drift back into interstellar space with leftover velocity, like a pebble flung from a sling. That property is not just a label, it shapes how we schedule our observations. There is no return cycle to make up for lost chances, no next time. Every measurement is one of a kind. The geometry of 3I Atlas is also intriguing, in that it tilts only slightly relative to the ecliptic. This carries it through the same patch of sky where planets and most solar system comets appear. The advantage, observatories already have the infrastructure aimed there every night. The drawback, on crucial days, it may lie close to the sun in our sky, forcing us to rely on coronagraphs to fill the daytime gap. At some points, you and I will follow it as a faint speck in the solar corona through public data, then wait until it slips far enough from the glare to hunt with binoculars or a small telescope. If you ask why 3I Atlas excites researchers so much, the answer lies in the weak light it gives off. As its ice sublimates, molecules are excited and shine at characteristic wavelengths. By splitting light into spectra, we can read those lines of physics. For most inner system comets, water dominates once they get close enough, bringing along familiar companion molecules. 3I Atlas tells a different story. Strong signals of carbon dioxide and other volatiles rise, while water vapor is much weaker. This may reflect the environment where it formed, where the temperature and the makeup of the protoplanetary cloud differed from the comet-forming zone of our system. Think of it as a recipe from another cuisine. It's still a soup of ice and dust, but with seasonings and proportions unlike our kitchen. The huge shadow of 3I Atlas in the sky comes from a phenomenon both familiar and strange. The solid nucleus may be small, but the gas and dust cloud around it, the coma, can expand to sizes comparable with giant planets if activity is strong. Hundreds of thousands of kilometers may sound beyond belief, but it tells a simple story. Under the sun, ice sublimates, gas puffs up the dusty shell, and fine grains are lifted and spread. A large coma is not a beauty contest. It is a sign of venting power and surface structure. With 3I Atlas, a swelling coma plus unusual chemistry is an invitation for big telescopes to gather every precious photon and decode the recipe. A practical question: will you and I hope to see 3I Atlas with the naked eye? The honest answer is uncertain. With a perihelion not too close and sometimes unfavorable geometry, it may be within binocular or small telescope reach rather than unaided eyes. But even so, its value does not lie in spectacle for casual viewers. It lies in the fact that every spectrum, every light curve, every record of its ion tail responding to the solar wind adds another slice to the comparison between native and immigrant material. There's another aspect not to overlook: non-gravitational forces. Any comet feels small pushes from its venting gases. With 3I Atlas, orbital modeling must include those parameters. But unlike inner-system comets, we don't have years of history to lean on. That makes every positional update precious. When astronomers announce that the orbit has been adjusted slightly with new data, you and I are seeing the outer skin of a deeper problem. Signals from a spinning nucleus, directional jets, and sublimation intensity all contributing. One more fascinating possibility: Earth could pass through a faint dust trail left by 3I Atlas in a later season. If that happens, and the dust is dense enough, the night sky might host a weak meteor shower of interstellar origin. No promise of fireworks, but scientifically, just confirming that such dust differs from inner-system dust would be worth pursuing. Atmospheric and meteor monitoring teams will be ready to catch those tiny grains as they flare in friction. I want to pause on the feeling 3I Atlas brings. Watching it, you and I can sense something strange. The solar system is not a sealed box. It has doors, and sometimes one opens. From that threshold, a visitor steps in, carrying the scent of elsewhere. We greet it with light and spectra, with graphs and models. That may sound cold, but it's the only way to hold on to a piece of the guest once it departs. A good data set is a postcard we can reread, each time with a new insight. As for you, if you want to hunt 3I Atlas, track its geometry closely. On some days, it will lie too near the sun in the sky. Don't force it then. Instead, watch coronagraphs to keep the story flowing. When it drifts far enough from glare, pick a clear horizon, use binoculars, employ averted vision, and be patient. Don't be disappointed if you see only a modest blur. Remember, you're looking at an interstellar gift material that has never been here before and won't remain. Recognizing it is already a small victory for your eyes and your curiosity. From 3I Atlas, the natural road leads us into the dialogue between comets and the sun in this active year. Ion tails will tell the story of wind, magnetism, and disconnections. Charged particle measurements will join your sky photos, showing how each piece of personal data links into the larger picture. You and I will move along that path, slow enough to understand, yet quick enough not to miss the fleeting moments. You and I have already looked at 3I Atlas as a visitor with an interstellar passport. Now let's spread the calendar out on the table, mark the key bends, and tie them to its chemistry to see why each milestone matters. From late October to early November, the geometry of 3I Atlas offers two moments that make skywatchers restless. First comes the phase when it lies behind the sun as seen from Earth, called the superior conjunction. At that point, it hides in the sun's glare, forcing us to set binoculars aside and switch to coronagraphs. Next is perihelion, a little beyond Mars's orbit, where the sun's energy is strong enough to push its activity up a notch, but still not close enough to trigger a dramatic outburst like the daredevils that skim the sun. In the sky, these two marks play out like a breath taken in and a modest flare, fitting for a guest that comes fast, visits fast, and leaves fast. The finest numbers of 3I Atlas aren't in dazzling magnitudes but in delicate spectra. When you read reports that CO2 dominates and water is weak, that's not just an ingredient list. It's a clue to its cradle. If a comet formed in the very cold zone of a protoplanetary cloud around a long-ago star, its stock of volatiles like CO2 and CO could be richer, while water might not always rule the first layer awakened by sunlight. Alongside its formation past is its migration present. Millions of years adrift in interstellar space mean its surface has been battered by cosmic rays, enriching it with unusual chemical radicals. When 3I Atlas comes here, our sun stirs that recipe, letting telescopes split the light into letters we can read. Its orbital geometry tells another story. With only a small tilt from the ecliptic, it takes a path more convenient for sky position, since observatories already watch that zone nightly. But the advantage comes at a cost. Key days often coincide with small elongations from the sun. At those times, you and I must settle for near real-time coronagraph images, where 3I Atlas shows up as a moving speck near the solar halo. There, don't expect grandeur, expect precision. Each frame carries position, angular speed, and sometimes a faint change in the ion tail when the solar wind shifts state. If you ask what to hope for once 3I Atlas emerges from glare, the realistic answer is a binocular target under dark skies, occasionally reaching small telescope range. The familiar comet shape is still there. A fuzzy head, a wide pale dust tail, a thin ion tail pointing straight from the sun. But because it isn't especially close and its activity is limited by the energy it receives, the naked eye impression will be modest. In truth, that modesty is the lesson. 3I Atlas teaches us to value steady light curves and sparse spectra, for those are the only ways to carry a fragment of a foreign world into our labs. On the modeling side, 3I Atlas is a fine exercise in non-gravitational forces. When jets vent gas to one side for hours or days, the orbit drifts slightly from the gravity-only line. Astronomers add 3 non-gravitational parameters along orthogonal axes to fit the data. For an interstellar body without a long history, each positional measurement carries extra weight. I like to think this is where even persistent amateurs can lend a hand. A time-stamped photo, marked against background stars and shared into tracking networks, may help refine the data stream. Other small mysteries lie inside. What is its rotation period? Are there dominant jets? Do brief outbursts come from shell cracking or fresh ice exposure? These are hard to answer clearly because 3I Atlas doesn't favor us with brightness. Hard doesn't mean impossible. Chains of short exposure images, stacked into a light curve, can sometimes hint at rhythm. A thinner than usual ion tail after a strong gust can hint at grain structure and ion ratio. Each fragment is a small plank. When enough are laid, you and I will see the bridge. For safety, let me repeat what's obvious but easily forgotten. Don't point binoculars or telescopes close to the sun by just a few degrees, unless you have filters specifically built for that purpose. With 3I Atlas, the most tempting times often fall near unsafe elongations. The best approach is to wait until it pulls far enough away or rely on space data. Human eyes have limits. Putting instruments in the right place is how we extend our reach without risking health. One branch of the story that delights many is the chance Earth might cut through a thin dust trail left by 3I Atlas. If that happens next year, a few nights might host a very weak meteor shower, more likely caught by atmospheric radar or all-sky camera systems than by the naked eye. Even without a spectacle, it's a scientific gem. Interstellar dust grains flaring give us velocity, retrograde orbits, and most importantly, composition if microfragments are collected. Imagining a speck from another system falling into our air, shining for 1,000th of a second and leaving a line of data for researchers shows the value of patient tracking. You can turn this season into a class of your own. In the morning, open public data streams of solar wind and the interplanetary magnetic field. Note the departure time of a solar eruption. Estimate the shock travel time to 3 atlases region. In the evening, if geometry allows, look up or check coronagraph images. A tail disconnection at just the right time feels like the clock in your head and the cosmic clock striking together. Experiences like that often turn video watchers into sky observers. On a personal note, I love how 3i Atlas makes us slow down. It isn't bright enough to seize you with spectacle. It draws you with meaning. Every photon you catch is a story fragment from another star system. Every spectrum a handwritten line in a stranger's script. You can't rush it. You can't push it to give more. You can only receive, record, and be grateful for the chance to touch a story usually confined to books on planet formation. From 3i Atlas, the road naturally leads you and me into conversation with the sun. As solar activity climbs toward maximum, the ion tails of many comets will become living compasses. Disconnections, fine oscillations, small surprises, these will line up like notes in music. We'll step into that plasma classroom in the next part, where solar storms aren't just headlines, but rhythms flowing through each pale blue streak beside icy nuclei. You and I have spoken about icy nuclei, about dust, and about an interstellar guest passing through. Now let's turn the camera toward the source of light that drives all of these stories. When the sun enters its maximum phase of activity, it resembles an ocean filled with storms. The outward flow of plasma, called the solar wind, never stops. In that flow, magnetic field lines coil into a great spiral wrapping around the system like invisible cords. Every small body, such as a comet, must cross. Each ion tail you see is really a stream of ionized gas, stretched straight away from the sun by that current. When a storm comes, the invisible cord yanks sharply, and you see the tails snap and regrow in a new direction. That isn't magic. It's electromagnetism in front of your eyes. 3 main actors take the stage. The background solar wind, made up of slow and fast streams, takes turns dominating depending on its source region on the sun. Coronal mass ejections, huge blasts of plasma and magnetic fields, are like bubbles carrying their own structures, racing through space as shockwaves. And the heliospheric current sheet, the giant magnetic boundary where polarity flips, is often compared to a rippling curtain cutting across the ecliptic. When a comet crosses any of these 3, its ion tail responds. Sometimes it's just a wrinkle, sometimes it's a clean slice. The physics of tail disconnection can be summed up in 2 words: sudden change. The magnetic field in the solar wind suddenly swings, while the comet's plasma cannot swing fast enough. At the edge of the tail, the old and new field lines collide. Where they reconnect in the most energy-efficient way, we call it magnetic reconnection. When that happens, the old tail is detached like letting go of a ribbon in the wind. It drifts away, fading. Meanwhile, a new tail begins forming in the direction of the fresh field. For you and me, in photos or through binoculars, this moment appears as a faint gap near the head, followed by a blurred strip peeling away, and a new, thin, straighter streak sprouting outward. What makes 2025 special is not only the number of comets but the timing. At solar maximum, storm events come more often. Instead of waiting weeks for a notable hit, you and I may see several in a month. That turns each comet into a traveling magnetometer. If many comets at once lie near the ecliptic, they act like barometers lined along a cross-section, each recording a version of the same flow. That means, if we follow them together, our odds of catching at least one beautiful tail disconnection rise sharply. One misconception I want to clear with you: when you see a spectacular disconnection, it's tempting to think the comet was struck or shoved by some strange force. In reality, the nucleus keeps gliding calmly on its orbit. What the magnetic play roughs up is the thin plasma far behind. Imagine a small boat trailing behind a big ship on a rope. A sudden gust may snap the rope, but the big ship still stays on course with its inertia and engines. A comet's orbit is ruled by gravity. The dance of its tail is the story of electromagnetism. To turn dry physics into experience, you and I can run a simple experiment. Each afternoon, check public space weather bulletins to note when a big solar eruption departs the sun. Estimate the travel time by solar wind speed. For the slow flow, think days. For fast streams or shock waves, sometimes only a little over a day. Mark the likely window when the impact should reach a comet you're following. The next night, look if you can. If not, watch coronagraph images. A tail cut on schedule is a reward for patience. You've just made two clocks strike together, the sun's clock and your own. Look closer, and you'll see not every encounter cuts a tail. Many times, it just bends more, ripples more, or grows small wrinkles. That too is valuable. It tells you the solar wind's order is a beautiful complexity. Tiny eddies, subtle shifts in density and temperature, all write letters on the ion tail. If you capture short exposure image series, you can stitch them into a slow movie where the invisible flow is drawn by glowing gas. One thing to remember, the dust tail differs from the ion tail. Heavier, it responds more to sunlight and gravity than to electromagnetic forces, so it reacts less to storms. If a strong hit does deform the dust tail, it's rare and worth recording, but don't expect it often. In practice, when you see the dust tail still soft while the ion tail thrums like a plucked string, you're seeing two films in parallel, telling the same story in different scripts. Another thought often arises when many comets appear together. Could they affect the sun in return? The gut says yes, since they throw plasma and dust into the stream like a handful of sand tossed into a current. But in energy terms, the sun overwhelms. What you and I see are mainly the tail's responses, not drivers of change. Of course, fine models still test whether small bodies seed local instabilities, but until data force us, the safe view is to treat comets as natural wind vanes, faithful to the direction and strength of the flow around them. In practice, what does this mean for you? First, learn to read the tail direction. The ion tail always points away from the sun. That helps you quickly identify the head and tail, even when the brightness is low. Second, watch the sharpness of the ion tail's edge. Thin and crisp means a calm environment. Ragged and diffuse means small turbulence. Third, record the time. A nice disconnection only has full meaning if you know when it happened, so you can compare it with solar wind data. Those notes turn wow into usable knowledge. On the emotional level, the best part of catching a tail disconnection may be the silence just after you realize it. You are watching a filament of gas, thin enough for starlight to pierce, cut by an invisible twist in the magnetic field of a star, 1 astronomical unit away. That distance and delicacy make us smaller and richer at once. Smaller because we realize we live inside a system larger than any hasty question. Richer because by simply looking up with understanding, we are in a classroom of nature with the sky as the textbook. Once you and I have grasped this rhythm, we can return to the comet swarm with different eyes. Each name is no longer just a target, but a measuring point on the solar wind and magnetic map of this maximum. In the next section, we'll align tail rhythms and storms with each comet's path, so you can craft your own observing plan. Which nights to step outside, which dawns to rise early, when to open a browser for coronagraph feeds, and wait for the invisible scissors to slice a thin tail. You and I have just covered the core physics of the ion tail. Now let's turn that into a workable observing plan, while also looking at the debate between modelers and near-Sun missions. I believe when you understand both sides, you'll have calmer eyes when seeing a split tail on screen, and steadier hands when setting up a tripod on your porch. At the heart of the debate is a very human question. Are comets just wind vanes, or can they slightly stir the very wind they trace? The modeling groups, especially those working in magnetohydrodynamic simulations, argue that when a strong comet passes through a complex magnetic structure, the plasma cloud it releases could act as a small obstacle, reshaping local field lines and perhaps triggering faster or sharper reconnection events. With many comets at once, they imagine a chain of natural experiments, each object as a possible spark for small instabilities. The argument sounds persuasive, especially beside images of crisp tail breaks captured by space missions. The near-Sun mission groups add a needed restraint. In situ field data show the heliosphere is ruled by grand structures, alternating fast and slow streams, shocks from eruptions, and the rippling current sheet. In that overwhelming energy landscape, a comet's little plasma cloud is unlikely to dominate. They note many cases where ion tails were battered and rattled without breaking, even in heavy turbulence. For them, comets are excellent tracers, but mostly passive. Science grows through such healthy tension, and you and I need not pick sides too soon. We can treat this season as a large field test, where tail images and field charts together write the answer. Your observing plan should start with the calendar. Sketch out days around each comet's milestones. For those too close to the Sun, mark coronagraph days. For those with good twilight windows, mark those dawns or evenings. Each day, spend 5 minutes on space weather bulletins. Train your eye to spot a solar eruption, a new fast stream, or a polarity flip. Estimate travel times. Then, in your notebook, draw a small arrow from the solar event to the comet viewing window. By nightfall, you have a hypothesis before looking up. Your equipment can be modest. A standard binocular, a tripod, and a camera able to take exposures of tens of seconds are enough. Consistency is key. If possible, take image sequences minutes apart in the same session so you can stitch them into a short film showing tail changes over time. Don't chase long exposures that blur the tail with motion. Shorter exposures, moderate ISO, and more frames work better. For direct viewing, practice description, head brightness, apparent tail length, edge sharpness, knots or bends, and always the time. Those notes, set against solar wind plots, turn feeling into data. Don't neglect coronagraphs. I know sitting at a screen feels less thrilling than stepping outside, but some of the best shows of the season happen there. As a comet crosses the field, you can watch the whole approach. The tails stretched, and sometimes the cut. If you save frames at regular intervals, you can stitch and measure angular speed. Here, you and I play by best condition rules, using machines placed where human eyes cannot stand, while keeping the careful record-keeping culture of classical observers. One principle I remind myself of: beware coincidences. If in the same week there's a strong solar storm and a flicker in your local power grid, it's tempting to link them, especially when your thoughts are full of the sky. But real connections must climb a ladder. Did a solar event occur? When did the shock reach Earth? What did magnetometers record? Did monitoring agencies issue alerts? You and I have the right to ask, but also the duty to check each step before telling the story. That spirit doesn't dim the beauty of this season. It makes the beauty meaningful. Let's add safety. When a target lies close to the Sun in the sky, don't observe directly without the proper equipment. Don't aim binoculars just because the Sun is behind a building. A tiny error in angle can cost your eyes. For near-Sun targets, give daytime to coronagraphs and let twilight be the safe window for us. If you observe near the horizon, pick an open view, away from exhaust, humidity, and headlights. A jacket, a warm drink, and a good chair will keep you outside longer. And those extra minutes often bring the frame you were waiting for. On the emotional side, something happens when you start syncing the Sun's rhythm with comet tails. The sky is no longer a still painting, it becomes a piece of music. Each disconnection is a note struck. Each thinning is a drawn-out chord. You stand in your yard, but in your mind is a cosmic orchestra, where satellite data, magnetic plots, and your faint streaks on photos blend. Once you taste that, watching turns to participating. And once you participate, This comet season will stay with you long beyond the clear nights. Finally, let your plan leave room for surprise. Comets are fickle artists. Some nights they whisper, some nights they burst. Science advances when we're there for both. You and I will continue with the next players of the season, including one visitor promising naked eye moments after sunset, if weather and sky allow. Before that, let's fold the map for a moment and remind ourselves, the greatest reward of a plan is being present at the right time, not controlling the result. If Swan invited you to rise early at dawn, then Lemon promises a reward in the evening right after sunset. You and I tend to love golden hour targets because they're friendly. Dinner is done, the sky is still painted pink, and low in the west-southwest, a faint blur trails a fragile tail. With perihelion in early November, Lemon falls exactly in that time slot. Cautious forecasts suggest it may reach naked eye visibility under truly dark skies around magnitude 4, perhaps brighter if geometry favors us. That doesn't make it a firework, but it is enough to turn an ordinary evening into a small rendezvous between you and the sky. Start with observing geometry. After sunset, Lemon sits low, so an open horizon is essential. Avoid city lights. Pick a field, a beach, a hillside where the view is wide. Even a few extra degrees of elevation at your observing spot can matter, since near the ground, humid, thick air scatters comet light, blending the tail into the grey twilight. I always recommend carrying an offline star map app set to real time, with red night mode to protect your eyes. Through 10 by 50 binoculars, you'll notice the comet's head as a fuzzy patch, brightest at the core, fading gently into the tail. A delightful aspect of golden hour comets is phase angle, the angle between sun, comet, and observer. When a comet hangs opposite the sun, right after dusk, forward scattering of sunlight on dust can boost brightness for a short interval. Think of dust in a room glowing when you look toward a sunlit window. With Lemon, a favorable phase angle may make the dust tail stand out more than predictions. It reminds us that magnitude tables aren't destiny. Sometimes geometry grants a bonus. Lemon is also a perfect stage to learn dust tails from ion tails by eye. The dust tail is broader, whitish or faintly yellow, curving slightly along the comet's motion, shaped by sunlight and gravity. The ion tail is narrower, bluish, pointing straight away from the sun, tugged by solar wind. After sunset, the ion tail is harder to spot, but as the sky darkens, binoculars may reveal a thin, straight filament stretching from the head. That's a basic yet powerful physics lesson drawn in the sky. If you'd like to go beyond watching, Lemon is a forgiving photo subject. A standard camera on a tripod, lens from wide to normal, exposures of 5 to 15 seconds can capture a tail longer than your eyes can sense. Don't overdo exposure comet drift and sky rotation blur it. Take many frames with the same settings and later assemble them to see motion against the starfield. If you can use filters that highlight cyanogen or ion bands, you'll separate tails more clearly, but it's optional. The key is consistency, since uniform series make comparisons easier across nights. Educationally, Lemon introduces you to the simple AFRHO index often mentioned by observers. Even if you don't calculate it yourself, tracking updates helps you distinguish true dust productivity from geometric illusions. Rising AFRO means real dust increase, often fresh ice, exposed or surface cracks. If AFRO stays level but brightness rises, think phase angle or darker skies. That habit trains your eyes not to be swayed by raw magnitudes. A constant question, might Lemon's outburst? Honestly, maybe. But please don't stake your heart on it. Comets are physically alive. Dust crusts can insulate, muting activity, yet one crack in the right spot may vent fresh ice, brightening dramatically for hours or days. Nights like that thrill, but also set fragile expectations. Better to keep a flexible plan. If alerts report a flare, step outside earlier. If not, the night is still worthwhile because you're building your own light curve. Lemon also bridges tail physics and space weather we just discussed. Solar maximum raises the chances of ion tail breaks. But at golden hour, low in twilight, it's harder to catch a clean disconnection by eye. That's where coronagraphs shine, follow them by day, compare with the real sky by night. If you record a slim, unusual ion tail right after a solar event hits on schedule, you've braided two worlds: space data and backyard experience. Practical. US notes. On the West Coast, marine haze can make horizons bright and muddy go inland or higher. In the Midwest, flat skies are great, but light pollution spreads wide. State parks an hour from town often pay off. In the Northeast, autumn's thin clouds are tricky. Pick dry north winds for clearer skies southward. Wherever you are, let your eyes dark adapt for 15 minutes, often the difference between seeing a faint tail or not. Emotionally, lemon carries a gentleness, a fuzzy smudge at day's edge, while cars and voices still hum around, reminds me that astronomy doesn't demand total isolation. Beauty can slip into daily rhythm, asking only a gesture. Look up and slow down. Maybe you'll invite a family member onto the porch, hand them binoculars, and watch their eyes widen as the tail stretches from the head. That moment is your reward, not found in any chart. In the end, lemon is a test of how we blend discipline and freedom. Discipline means checking forecasts, prepping gear, and keeping notes. Freedom means letting yourself be surprised, letting a chilly, ordinary evening still count as a win because you were present. Hold both, and you'll see each comet as a character with personality, and the whole season as a coherent story. After Lemon's golden dusk, you and I turn to a quieter character, valuable as an anchor, a periodic comet from the NEAT family. In a year of sharp flybys, scorching perihelia, and even an interstellar guest, NEAT reminds us of astronomy's steady rhythms. It isn't here to make headlines. It is here to give us a baseline, a metronome tick within a swelling symphony. First, let's read the name. In comet designations, P means periodic confirmed to return after many years. The number before P is its catalogue order among numbered periodic comets. The name after the slash often honours the survey or discoverer. In this case, NEAT, short for Near-Earth Asteroid Tracking, a project aimed at hunting near-Earth asteroids that discovered many comets along the way. Contrast this with C for non-periodic, or 3I for interstellar. Reading the name isn't just a ritual. It drops the object into the right drawer, returning regularly, with stable geometry, rarely flaring dramatically. Orbitally, most neat comets belong to the Jupiter family, meaning their Tisserand parameter with respect to Jupiter falls in a familiar range of orbits controlled by the giant planet. This means gentle tugs each passage, shifting perihelia and periods slightly. For us, the practical meaning is slow orbital evolution, no sudden turns. Subtle changes logged across returns, sometimes modelled with non-gravitational terms when sublimation adds small thrust. Highlight this season. NEAT's perihelion is far, outside harsh solar heating. That places it in the good binocular to small telescope class, leaning toward telescopes. It appears modest, fuzzy head, faint dust plume, maybe a whisper of ion tail. So why care? Because such calm light curves are the baselines. When you see NEAT alongside a fiery visitor like Atlas K1, you grasp instantly the roles of solar energy and geometry. Same sky, same observer, differences traced to orbital physics. NEAT whispers that not all is storm. Some limits are set by distance and composition. Observing NEAT honors classic star hopping. Instead of a bright dot popping from the background, you'll use a detailed chart. Step your scope through asterisms, confirm fields, and stop where a misty speck should be. This is where averted vision shines. Eyes detect faint sources better off center. Give your eyes 5 to 10 minutes to adapt. and neat will surface from grey. A 4 to 6 inch scope is ideal, enough light to show head and stubby tail, small enough to haul into the yard on cold nights. Speaking of cold nights, US observers will meet NEAT under winter skies. The good news, early darkness means no late bedtime. Try a state park an hour outside the city. On the west coast, fog is your foe seek dry hillsides. In the Midwest, dry cold is a friend bring dew shields. In the Northeast, wait for north winds to sweep clouds. Wherever you are, a dew strap, hand warmers, and thin gloves that still handle eyepieces extend your sessions, and that's the real variable. Scientifically, NEAT is a doorway to AFRO. Its steady brightness makes small AFRO changes more meaningful real dust output, not geometry tricks. Even if you don't compute it, following community reports trains you to recognize stable so you can judge others. Maybe one night AFRO ticks up slightly after a minor flare. Instead of a miracle, you calmly log another curve point and smile. You've read a quiet comet's voice. At the plasma scale, NEAT's distance makes ion tails subdued. But that means any clear distortion you log is precious, telling more about the wind than the comet. Note a solar shock's ETA, then check the next night for thinner or angled tails. Even a no change matters, it strengthens the map. Not every solar kick leaves a scar. NEAT also teaches statistics. A quiet baseline in a season of specials lets you separate signal from noise. If social media erupts over a sliced tail on a brighter comet, spend a few minutes on NEAT. If it shows nothing odd, maybe the event was local, or processing, or a real gust that simply missed. NEAT. Parallel comparison is a powerful critical tool, and NEAT teaches persistence. No single night is a firework, but weeks of notes build value. When NEAT returns next cycle, you can lay new curves atop old and see science in your own handwriting. That is a rare feeling, turning you from spectator into participant in a measurement chain longer than weather or mood. Emotionally, NEAT is a whisper that the skies are lovely, not only in rare peaks. They're lovable on ordinary nights, when a faint speck slows your breath. In a year with 7 visitors crowding and 1 interstellar riddle, giving time to NEAT is like hearing a familiar melody after a drum solo. It deepens the song. It gives you grounding to savor the crescendos. From NEAT, you and I will have material to step into the second half of our tale, why this year is so rare, and the debates about risks, benefits, and wild hypotheses swirling online. But before diving into the noise, take another night for a calm, faint smudge. You'll find the heartbeat of the sky steadier than our imaginations. You and I have walked together through each visitor from Swan's close pass at dawn, to Lemon's golden hour shimmer, to the interstellar guest 3-eye atlas. But the larger picture leaves us with one core question. Why so many, packed into one short season? This isn't a random laundry list. It's closer to a moment when the different clocks of the solar system strike in unison, and human eyes can hear it. We call this a windowing effect, layered across 3 levels: dynamics, geometry, and psychology. The first level is dynamics. Every comet's story starts with tiny nudges, gravitational whispers at the solar system's edge or beyond. Over millions of years, these nudges either send an object inward or not. Statistically, those departure times are scattered. Yet from Earth's viewpoint, scatter doesn't mean even spacing on our calendars. The reason is geometry. A comet only lodges in our memory if 2 conditions align, bright enough and well placed in the sky. In 2025, many orbits that began as separate stories happen to cross visibility zones at once, helped by a sun in maximum activity that makes ion tails stand out more. That's how individual tails fuse into a single headline. The second layer is geometric windows. Perihelion only says how close to the sun an object passes. Whether you and I actually see it depends on separation from the sun in the sky, altitude above the horizon, moon phase, and local weather. Some comets blaze, but cling too near the sun to be spotted. Others, modest in brightness, become events if they appear away from glare, right at dawn or dusk. In 2025, several such windows stack within weeks. Swan at dawn near Earth, Lemon low at dusk, Atlas K1 skimming near solar glare with a few gaps, and 3i Atlas hugging the ecliptic where telescopes sweep routinely. Windows don't stay open long, but if they overlap, it feels like a parade. The third layer is psychology. Our brains crave sequences. You and I remember eventful nights far more than empty ones. When rare happenings bunch up, both memory and social algorithms amplify the unusual feeling beyond dry statistics. Even a random scatter produces clusters. Just like the birthday paradox, put 30 people in a room, odds of a shared birthday are high. Here, the birthday is a clear, visible night. In 2025, the count of clear window comets crosses the threshold where clustering feels inevitable. The rarity lies less in physics than in several secondary conditions aligning. Still, not every year can be jammed together like 2025. The uniqueness rests on two underlying conditions stepping on the same pedal: solar maximum, which enhances tails, and survey capacity, which now misses a few faint comets. Robotic sky scans are faster and deeper, pulling once random finds into early watch lists. But more discoveries don't automatically mean more brightness. The beauty of 2025 is that enough of those finds also fall into good visibility geometry to make a season. Two vectors in sync, both gates swung open. You can measure the rarity with simple handholds. First, naked eye threshold, around magnitude 6 under dark skies. 2025 has at least one borderline candidate slipping across that line. Second, binocular count. If 2 or 3 comets in a month are within reach of basic binoculars, your experience changes. It's like autumn leaves. A single tree is lovely, but a whole forest changing together makes a season. Third, ion tail events. Solar maximum lifts the chances of disconnection. Instead of once a year if lucky, you may see once every few weeks. A common myth: solar activity drags comets inward. Not so. Inbound journeys come from long-term orbital nudges. Solar maximum only adds lighting and wind, making actors look louder. It doesn't write the script. We should separate why they arrive from why we see them. 2025 answers the second. The first belongs to timescales far beyond human memory. Another subtlety: ecliptic geometry. When several low-inclination comets share the ecliptic sky with planets and familiar stars, the effect is connection. In one evening, you can sweep from a comet fuzz to a bright planet and back to another comet. That continuity builds collective memory, helping the season last longer in culture. For me, layering these factors doesn't suggest a hidden hand. It shows a natural festival of probability, geometry, and technology. Rare, because 3 gears mesh at once. Rare, because our tools are sharp enough to notice. Rare, because memory yours, mine, and the networks we share keeps the lively nights longer than the quiet ones. That doesn't make 2025 less magical. It makes the magic legible, and legible magic is even more precious. From this rare picture, the logical next step is risk. Does such clustering threaten satellites, navigation, and power grids? In the next section, you and I will draw a clear line, distinguishing solar storm technology risks from impact fears that have no basis this season. We'll hold on to wonder, but keep it beside evidence. You and I agree, 2025 is rare because visibility windows overlap, but lively skies always spark unease. Are we in danger? Will satellites, GPS, and power grids suffer? And the most common fear impact? Let's lay the worries on the table. Sort science from feelings. Start with the solid. Impact is not the story this year. Orbits are computed with high precision. These comets pass at tens of millions of kilometers. They are not inbound. They pass, then leave. When a shocking headline claims otherwise, remember a rule. If real risk exists, official trackers publish specifics, probabilities, dates. If you only see vague words, breathe deep and check the data. The real arena is the sun. Solar maximum means more flares, more plasma, and magnetic storms. When these reach Earth, they trigger geomagnetic storms. Not sky is falling, but disruptive for our tech woven of electricity, magnetism, and radio. 3 main pathways: radiation spikes in space, ionospheric turbulence that bends radio-shouted GPS signals, and geomagnetically induced currents in long power lines. For satellites, the picture is risky yet manageable. Energetic particles can glitch electronics, forcing reboots, dropping links for minutes to hours. Heated upper atmosphere adds drag, lowering low-orbit satellites. Operators rehearse responses safe mode during storms, delaying sensitive maneuvers, adjusting orbits. So when you hear of a brief outage, don't panic. Most recover, and procedures exist. For GPS, the issue isn't broken satellites, but signals through a stormy ionosphere. Delays and distortions raise errors more at high latitudes, more during strong storms. For you, it may mean your map lags, or telecom networks adjust timing. Precision users, farmers with autonomous gear, surveyors watch disruption indices and pause work. For daily life, know that if GPS wobbles when aurora flares, that's space weather, not your phone. Power grids carry the heavier sounding risk, but it's also managed. Strong storms induce currents in long lines, entering big transformers. Unprepared, they can overheat, trip, or cut power. Utilities have learned from history. They monitor warnings, lower load before storms, and reconfigure grids. Outages still happen, but resilience is better. For you, the realistic prep is a flashlight, a charged battery pack, and calm if lights flicker during an aurora. Aviation also adapts. Polar flights sometimes reroute lower to reduce radiation and keep the radio steady. Again, this isn't comet-driven, but solar. The comets are wind vanes. The sun is the wind. On the personal level, the lesson is asking the right 3 questions when storms are forecast. How strong? What magnetic orientation? When arriving? Those matter more than comet counts. If curious, learn simple indices. Kp for activity, higher means stronger. DST for magnetospheric dip, more negative means deeper. AE for polar auroral activity. You don't need to be a pro, just knowing numbers exist gives you ground when headlines shout. A trap is timing overlap. Comet season and solar storms coincide. A tech glitch happens, and people blame comets. But the chain is solar eruption arrow, magnetic orientation arrow, Earth arrival time, arrow, geomagnetic record arrow, tech impact. Skip the chain, jump to blame, and you lose the learning. So what can backyard observers do? First, update yourself, but lightly. A few minutes a day checking space weather forecasts, logging KP, and expected arrivals. Second, plan comet sessions safely, never pointing optics near the sun. Third, keep notes, not just beauty, but times, conditions, tail details, so later you can match them to solar data. That turns your night into a data point in the larger mosaic. Being a brick in the wall of understanding is as rewarding as a great photo. From my side, I see 2025 as a rare chance for America to talk science calmly. Auroras may dip to lower latitudes. A few digital services may stutter. The sky may show strange streaks. All are slices of the same orange. They don't call for fear. They call for a correct understanding. When you tell your child that a tail broke because solar fields flipped and GPS lagged because the ionosphere rippled, you plant a seed of awareness no viral post can replace. To close, the risks this year aren't icy rocks colliding. They're the sun's faster tempo, while we live inside an electric, signal-woven civilization. The good news, we know the playbook. We have warnings. We have responses. and we have the joy of linking data with skywrite from the porch. Next, you and I will pivot to psychology and culture. Why do humans always layer meaning onto streaks of light at night? Why does social media turn a rare astronomical season into a collective story thick with speculation? We'll respect that emotional history while keeping our compass pointing to evidence. You and I have talked plenty about orbits, ion tails, and tripods on porches. But another current always shapes how we experience a rare comet season: psychology and culture. When multiple smudges appear at once, the human brain rushes to build a story. That isn't just a habit, it's an ancient survival mechanism. Our ancestors thrived by overreacting to rustling grass like a tiger, rather than missing real danger. So the brain favors pattern detection, even when the data is only wind. The sky of 2025 is not just physics, it's a mirror reflecting the storytelling habits humanity has refined for millennia. Take a slice of history. In ancient China, chroniclers called comets broom stars, omens sweeping away order. In 1066, a bright comet appeared near the Norman invasion of England. Memory fused the two into destiny. In 1910, Halley's return met with tabloid rumours of poison gas in its tail, prompting people to buy bottles and antidotes. Not ignorance, just faster rumour than verification, and a mind craving neat answers to strangeness above. The pattern is always the same: rare sky, tense society, meaning attached. In the 21st century, the engine is an algorithm. Digital ecosystems reward mystery, urgency, and controversy. A video of a tail cut by solar wind gets cast as intervention because human intuition prefers intent to coincidence. The truth is, electromagnetism, the gut feels a hidden hand. Here, biases whisper, pattern-seeking stitches stray dots into lines. Attention bias recalls stormy nights more than quiet ones. Confirmation bias cherry-picks supportive fragments. And the classic fallacy, after means because, glues together unrelated events. A solar storm after a comet sighting. The brain ties them. The real link is the sun. My best exercise is to translate emotion into questions. Every viral claim, I ask, what mechanism is offered? What measurement could confirm it? If true, what prediction follows for next time? These don't kill wonder. They filter wonder into knowledge. They let you and me move slower in a world that spins too fast. Skepticism isn't cynicism. Most storytellers online aren't scheming. They're doing what humans do: search for meaning. Many curiosity-driven channels have become bridges to science, but attention is a contest. So we need small habits. Look for numbers, not just images. Hear explanations, not just headlines. Check expert quotes in context. These soft filters keep the essence, skim off the froth. I remember my first tail disconnection like someone snipping a green thread. My heart raced, and I wanted to assign cosmic intent. A friend pinged me. Check solar wind data. Perfect match. The wow remained, but now woven into a larger score. It wasn't the mystery's hand, but the sun's clock. Strangely, the wonder deepened. I had learned to hear a language. In America, where science culture and speculation culture both thrive, this comet season is a stress test. One side, amateurs pooling photos, logs, data building a shared beauty. The other, exaggeration, fear bait. They don't cancel each other. The wise path is to feed the first while listening to the second, so we know what to explain clearly. One doorway I urge: make viewers participants. Have children or students keep sky journals, 2 lines each night. What they saw, how they felt. Add a column for KP or solar storm alerts. Weeks later, they'll see links between faint streaks and space weather graphs. No lecture substitutes for joining 2 distant dots yourself. Culturally, seasons like this are rare teaching chances. Science museums, clubs, and observatories can host nights of guided sky watching. No fancy gear, just a narrator who knows when to speak and when to let silence teach. Most people don't lack curiosity, they lack an open door. The sky is open. Our job is to stand on the threshold and offer a hand. So psychology and culture aren't vague overlays, they're structural to experience. They explain why rare seasons become phenomena, and they give us a duty, retell with warmth, but grounded in mechanism. That doesn't kill mystery, it makes mystery accessible. In the next part, we'll wade deeper into speculation, extreme theories, alien probes, doomsday, disguised invasion. You and I will test them by evidence and prediction, keeping a balance between imagination and science. When the sky is busy, imagination is busier. We've spoken about meaning-making and algorithms. Now let's face the three loudest extreme ideas. 3I to Atlas is a probe, 7 comets mean doomsday, and an invasion hides in disguise. Let's treat each as a method test. What mechanism is claimed, what evidence could be gathered, and what predictions check out. That way, we preserve both curiosity and discipline. The probe idea appeals because it answers a deep craving. We're not alone. Arguments start with 3I Atlas being odd, hyperbolic orbit, unusual chemistry, early coma, low inclination. Some leap to artificial. If that's a model, it must yield testable results. First, materials. An artificial object should betray alloys or spectra unknown in natural ice. None so far. Second, dynamics. Propulsion should show in course changes beyond sublimation jets. Models track those curves closely. Unexplained deviations would be a red flag. Third, signals. A probe talks. SETI. Ears are open. Absence of repeated, modulated, narrowband signals is weighty silence. So, until such data, 3I Atlas is best read as chemically unusual, not engineered. The doomsday idea thrives on clustering. 7 comets, solar max, fragile grids, tech reliance. Here, split two worlds. Orbits are gravity's cold hand. They show safe passes, no impacts. Risks lie in solar storms real, but electromagnetic. A tailbreak doesn't predict your state's blackout without the chain. Eruption, magnetic field, Earth impact, magnetometer, grid. The right response is not panic, but readiness. Flashlight, backup battery, check KP. Let grid and satellite operators handle the manuals they've rehearsed. The invasion idea is strong in narrative terms. It casts Comet's silence as camouflage, 7 disguised craft, 3I Atlas commanding, sliding in along the ecliptic. Test it as with probes, but multiplied, coordinated brightening, synchronized course tweaks, cross signals. Instead, we see each comet with its own perihelion, chemistry, and solar wind reaction. Tail events match storms, not orders. Strategically, one must ask, why invade this way, when tech that arrives here already outweighs ours? A perfectly hidden fleet that fools both spectra and orbits requires heavier assumptions than the data demands. So are all expansive theories false? I'd say, not needed yet. Science doesn't forbid imagination. It demands imagination to pay in prediction and evidence. If someone claims Atlas is a probe, ask, what will it do when, so you can check. If 7 is a fleet, what minimal coordination would show? If doom is near, what scale, mechanism, timeline? When answers are stories without numbers, file them accordingly. Our pull to such theories is natural. They pluck strings, fear of surprise, hope for company, hunger for order. I don't want to erase that emotion. I want to set it beside another joy, seeing mechanism laid bare. A tail cut, matching a solar shockwave, is as grand as invasion tales, because there, you've touched a star's language. So what do we do with the mystery left? Keep it, but use it as an engine for sharper watching. If you suspect odd behavior, join tracking networks, submit time-stamped images. If you think 2 comets show coordination, frame them together over nights and compare tails with solar wind data. If you worry a storm may hit, follow official alerts and log your real experience. That way, Stories become small experiments, and you contribute data yourself. For teaching, this is gold. Kids can learn the rare truth. Science doesn't kill wonder. It preserves the wonders that can be repeated and shared, and leaves space for the rest without filling it with flashy guesswork. Teach that, and they'll learn to savor busy skies without hidden hands to justify awe. My confession, I like to imagine 3i Atlas as a postcard from another system, but precisely because I value that postcard, I want to read its letters clearly, through spectra, light curves, ion tails whispering solar wind. If someday another parcel arrives with handwriting unmistakably from intelligence, we'll know because we trained our eyes on unnatural signals. Trusting data is the surest guard against missing what's truly extraordinary. From here, we'll swing back to other members of the swarm, especially Atlas K1 and stereo near-sun characters, promising tales rich in drama. You and I will map schedules to viewing hours, turning this rare season into a night-by-night journey. You and I have spent time with comets friendly to the naked eye. Now comes Atlas K1, a fiery personality, perihelion, dangerously close, geometry lost in glare, activity swinging fast with the moods of solar storms. This is not a comet for lazy evenings on the porch. It demands both halves of the brain discipline with instruments and intuition for fleeting moments. Expectations first. With perihelion at roughly 1/3 of an astronomical unit, Atlas K1 soaks in fierce sunlight. But the best physics happens when it hugs the sun in the sky, too close for binoculars. Strategy shifts from backyard to screen, coronagraph cameras first, then slim twilight windows when elongation is just enough to glimpse it above the horizon. Except that two-step dance, and Atlas K1 becomes a rich teacher. On coronagraph feeds, train your eye for 3 signs. A taut, ion tail suddenly snapping near the head, textbook magnetic reconnection, gentle ripples down the tail, turbulence in the solar wind, slight misalignment from the exact anti-solar line, geometry mixing with field shifts. Every time-stamped screenshot you save is a tiny measurement. The science of a blazing season is built from such bricks, in those thin dawn and dusk windows, horizon and safety rule. In the US, west-southwest after sunset or east-southeast before dawn are your best shots. Beaches, ridgelines and flat plains beat city skylines, but never swing optics near the sun unless it's at least 10 to 12 degrees below the horizon, or you have certified filters. Eyes are irreplaceable. Atlas K1 is also a stage for dust versus ion reading. The head compressed sunward, a faint curved dust fan, a straight ion filament all tell complementary stories. Dust speaks of the nucleus and AF-Rho. Ions speak of the solar wind. One twilight can teach both languages. For imaging, think 2 tracks. Track A, coronagraph frame series to build rough light curves and catch disconnections. Track B, wide angle or 50 to 85mm lenses in twilight, 5 to 10 second exposures, many frames, not long ones. Dust tails will stretch farther than the eyes suggest. Narrowband ion filters can highlight the green-blue filament, but consistency in settings matters more. Near perihelion, non-gravitational forces peak. Strong jets act like miniature thrusters, shifting position by measurable ticks. Modelers add A1, A2, A3 to equations. You needn't calculate, but know your precisely timed image might shave uncertainty from an orbit. Atlas K1 is a citizen science chance. During solar max, Atlas K1 becomes a synchronization game. Note a coronal mass ejection, estimate travel time, and watch the tail at the right hour. Not every attempt yields fireworks, but some do, and when prediction matches sight, you've tasted the quiet joy of science in action. Manage disappointment wisely. Some near suns never flare. That too is data, a well-insulated crust, low volatiles, or unfavorable phase angles. Flat light curves still speak. and they make surprises sweeter if they come. For Americans, Atlas K1 is an excuse to explore the world of public data, coronagraph streams, KP indices, solar wind charts, and your own images line up into a map of meaning. Tell a friend that tonight's tail fluttered because of a solar shockwave 2 days ago. You've turned wow into a living lesson. My own feeling with Atlas K1 is that of someone peeking backstage. You never see the whole play, only slivers through curtains. But that incompleteness makes each glimpse precious. Atlas K1 teaches love of fragments and disciplined imagination for the rest. Next, we move to stereo, where a solar observatory's coronagraph, never built for comets, became a comet hunter, and an inclined orbit lets us see what backyards rarely can. You and I are used to porches, binoculars, and short exposures, but some visitors don't shine in backyards. Stereo is one, low, tilted, lost in glare. To the naked eye, it's a blur. Shift to spacecraft cameras at the sun's rim, and the picture blossoms. There, comets become live weather vanes in dense solar plasma. The stage is coronography. A disk blocks the sun, revealing the corona, waves of ejected plasma, and small nuclei trailing ion tails. Heliospheric images extend the view outward. Stereo's orbit dips below the ecliptic, crossing these fields often. By following public feeds, you and I borrow the eyes of space observatories from our living rooms. Stereo's magic is perspective. Near the sun, plasma changes hour by hour. On coronagraphs, you see tails snap within frames, ripples racing like plucked strings, disconnections timed to solar wind shocks. Stamp the clock on each frame, cross-check with models. You're doing live heliophysics. 3 habits matter. First, keep a calendar. Mark Stereo's perihelion week. Note when feeds update in your time zone and harvest images regularly. A week later, you own a film strip. Second, read the whole frame. Corona smooth or ragged, shock fronts passing, light artifacts. Then turn to the comet tail direction, gaps and ripples. Third, tie events to storms. From a tail snap, rewind days to a solar eruption, then check orientation and travel time. Sometimes it matches uncannily, sometimes not. Both teach. Stereo also sharpens geometric sense. Ion tails point anti-solar, but the perspective from below the ecliptic makes them look skewed. Dust tails fade in certain scattering angles. Knowing this avoids false mysteries. Want to level up? Plot head positions from frames. Convert rough pixel spots to angles. A smooth track shows the orbit. Tiny periodic wobbles may reveal jets. Suddenly, the nucleus feels like a character, not a pebble. Safety reminder. Never chase stereo near the sun with optics. Even post-sunset glare can sneak into a lens. For these targets, let the spacecraft watch by day and save your eyes for safer skies. Stereo reminds us, missions aimed at the sun become comet hunters by accident. Point a camera long enough near the star, and icy visitors stroll through. Good tools answer old questions and pose new ones. In America, this is family science at its gentlest. Show your child a faint streak dancing in real-time images. Say, this is the sun's wind, drawing lines we can watch now. No textbook beats that. Then step outside, look toward the hidden object sky patch, and smile, because you know the story continues. For me, stereo feels like listening to a storm through a window, close, yet safe. Each tail snap is a click in my mind, 2 clocks in sync, the sun's and ours. That's enough to make me close the laptop, breathe night air, and feel gratitude that we live in a time when comets and solar storms can be watched together. Next, we return to the centerpiece, 3i Atlas, where alien chemistry and hyperbolic paths ask more questions than answers. You and I have lingered at the sun's edge, watching Atlas K1 and Stereo perform in solar wind. Now we step back, take a long breath, and open the strangest envelope of the season, 3i Atlas. That tiny I stands for interstellar, a passport that cannot be forged. Until now, our stamp book held only 2, a mysterious cigar-shaped traveler in 2017, and a clear-tailed visitor in 2019. 3I Atlas is the third, but unlike its siblings, it wears the unmistakable cloak of a comet, a soft coma, a slender tail, and most captivating, an alien chemical accent. Let's settle the geometry first. Its orbit is hyperbolic, eccentricity greater than 1, meaning it is not bound, never to return. Picture the sun's gravity as a valley. Native comets loop endlessly inside, but 3I Atlas is a runner cresting the ridge, gliding across the valley and vanishing beyond. The key number is its hyperbolic excess velocity, small yet steady evidence that even far from the sun's pull it keeps its own speed. Orbital fits all agree. This is a passerby. Its inclination, only about 5 degrees, lets it move along the same plane as most traffic, blending in with local comets, but still on a one-way path. That orbit sets a timeline. On October 21st, 3I Atlas disappears into superior conjunction, hidden behind the sun. A week later, on October 29th, it swings through perihelion at just beyond 1 astronomical unit inside Mars's orbit. From our perspective, it's like hearing a friend's voice from behind a mountain, then seeing them emerge into view at the most dramatic moment. You and I can't see it by eye during conjunction, but coronagraphs will keep the story alive. When it drifts free of glare, slim twilight windows will allow binoculars or small scopes to catch it. The season of 3I Atlas is one of patience, not fireworks. Chemistry is what makes astronomers lean forward. Its spectra show a coma rich in carbon dioxide, weak in water, and cyanogen barely whispering. Native comets usually roar with water close in, while CO and CO2 dominate far out. Here, the script is flipped. 3 possible stories. 1. It was born in a nursery rich in volatile ices, where water was not the star ingredient. 2. The nucleus has a porous crust that traps water, but lets CO2 escape first. 3. Its thermal pass differs, perhaps baked gently in its home system before ejection, leaving an insulating shell unlike local stock. No single answer is forced, but every spectral line is a signature from a different planetary kitchen. That's why scientists set alarms for pre-dawn observations. Its nucleus size is uncertain, anything from a few hundred meters to a few kilometers. That ambiguity is a lesson in itself. A swollen coma, hundreds of thousands of kilometers across, can mask the tiny rock at its core. Best practice: combine light curves, total brightness over time, with narrowband spectra, individual gases. Overlay them, and you can tell whether a brightening is fresh ice or just scattering geometry. Dust tells its own tale. Every comet leaves a fine ribbon of particles along its path. For 3I Atlas, Earth may cross such a ribbon next year. Don't expect a meteor storm, maybe only radar blips or faint streaks on ultra-sensitive all-sky cameras. But scientifically, that's priceless. Measuring dust from another star system with our own sensors. Even 1 grain writing its curve in Earth's upper atmosphere would be historic. Non-gravitational forces matter too. As jets erupt from sunlit patches, they push the nucleus like tiny thrusters. Modelers fit parameters A1, A2, and A3 to account for this. For an interstellar object, measuring these shifts tells us about spin, surface patchiness, and cohesion. Every precisely timed photo you take is a puzzle piece in that equation. For US observers, the season splits into 2 halves. First, coronagraph watching during solar conjunction. Later, twilight sessions with modest optics. In the first half, habitually check spacecraft feeds, stamp times, and note solar activity in the background corona. In the second, keep expectations modest, a faint smudge with a short tail in a small telescope. If it bursts, you'll celebrate. If not, you'll still add data. And the lingering question, could this be artificial? Tempting, but fairness means waiting on evidence. A craft would reveal exotic alloys in its spectrum, maneuvers inconsistent with sublimation or radio transmissions. None has appeared. Until they do, The most respectful approach is to read the real script lines of spectra, positions, tails, and scattering angles. I prefer to think of 3i Atlas as a postcard from afar. The handwriting is physics, not intent. Piece together enough lines, and you'll read its greeting. Emotionally, it feels like standing on a beach at night, watching a distant ship slide across the horizon. You know it won't stop. You wave, but it sails on. Still, that passage becomes your memory. The night you heard an engine faint across the sea. 3i Atlas will leave us like that. A few images, a data set, a graph line, and a reminder that our solar system is only a convenient phrase. The roads beyond run much farther. Next, we'll lean closer to the handwriting itself. How spectra tell stories of birthplace, why CO2 sings before water, and what comparing 3i Atlas to its two interstellar siblings really teaches us. We've opened the envelope of 3i Atlas. Now let's spread the letter and read the script. Reading a spectrum is like reading handwriting, every line a stroke, every ratio a habit. The verdict: CO2 lines glowing early, water lines weak. That isn't a slogan. It's the product of careful subtraction, calibration, and comparison with comet libraries. Why does CO2 speak first? Imagine the nucleus as layered ice. If its outer crust is porous or baked, CO2 molecules slip out easily, while water waits for deeper heat. Or perhaps the nursery was colder, carbon-rich, so water was never king. Either way, it points to a different thermal and chemical history, a recipe book not our own. Comparisons help. One sibling, the 2017 visitor, lacked a coma, sparking debates over shape and sublimation. The 2019 sibling behaved like a classic water comet. 3i Atlas sits between, cometary, yet chemically unorthodox. That tells us the universe doesn't follow one recipe for comets. Same label, different kitchen. Spectra also carry clocks. Molecules glow for lifetimes before photodissociation breaks them apart. Lifetimes vary with species and distance. So, line strength is both a kitchen note and a weather report. Each spectrum is part nucleus diary, part solar wind snapshot. Uncertainty about nucleus size remains, but that's useful. It forces reliance on indirect clues. Light curve wobbles from rotation, jet activity cycling in and out of sunlight. Even modest telescopes can contribute. Carefully timed image sequences stitched into light curves are welcomed by professional teams. Dust trail? Yes, another signature. Earth may graze it next year, likely not fireworks, but radar echoes or faint streaks could still confirm interstellar dust. Imagine a desert radar station catching a tiny ping, aligning it with predictions, and realizing you've touched alien grains. That's planetary science. A faint blip, a penciled line, a smile in the control room. The plasma story matters too. 3i Atlas's ion tail is a harpstring plucked by solar storms. With the sun at maximum, the chances of witnessing a disconnection event are real. The science is in timing, stamp the moment. Trace back to a coronal mass ejection and link cause to effect. It's a perfect classroom exercise. One group tracks comet images, another follows solar indices, and then overlays the results. Suddenly, cause and effect leap off the page. What does all this give us beyond curiosity? Knowledge. Every insight into interstellar comet chemistry expands models of how planetary systems form and recycle matter. Locally, understanding non-gravitational forces refines orbit predictions for bodies that might someday matter. Globally, a grain of alien dust burning above Earth is a once-in-civilization probe of primordial material. Practically, here's what you and I can do. First, follow conjunction and perihelion schedules. Save coronagraph frames daily. Second, as it emerges, build a personal light curve with wide field shots using consistent settings. Third, Log suspected tail disconnections with precise times. Fourth, join positional networks if possible. Each time-stamped image sharpens orbital fits. My own view, 3-eyed atlas tests whether we can balance wonder with discipline. It's easy to swoon over the interstellar label or to strip the poetry into sterile numbers. Better is the middle. Let yourself shiver at the thought of alien dust touching Earth, then write down time, direction, and conditions. Together, wonder and rigor turn one night into a brick in the shared wall of knowledge. So from 3-eye atlas, we've learned to read a letter in unfamiliar handwriting. Next, we'll return to the sun and its storms, digging into tail disconnections, solar maximum's role, and the debate between bold models and cautious data. From there, we'll map all the season's characters onto the living plasma stage they share. You and I have read 3-eye atlas's handwritten letter in spectra. Now let's lift our eyes to the backdrop that makes every line bolder. Solar maximum. The year 2025 isn't one where comets are mysteriously dragged inward. It's a year when the stage lights grow brighter and the wind blows harder, every ion tail becoming a weather flag in space. When you hear tail disconnection, think of it as a short, dramatic tale of electromagnetism. A magnetic field flips, wrapped field lines snap, reconnect, and the old tail drifts away like a ribbon torn free. Step by step, the stage unfolds. A comet carries a thin, ionized atmosphere. The solar wind streams past, dragging the interplanetary magnetic field in a spiral. Field lines drape around the comet's ionosphere, stretching a magnetic tail behind. Normally, it points straight from the sun, the blue line you've seen in images, but the wind is never calm. A coronal mass ejection erupts, or the comet crosses a sector where polarity reverses sharply. Tension builds. Field lines twist in opposite directions until they can't hold. A small reconnection region forms, where magnetic energy becomes motion and heat. Plasma physicists call this magnetic reconnection. The result? The tail severs. Near the nucleus, a gap appears. The old tail drifts away. A new one grows along the new magnetic direction. To picture it, borrow some keys. Kelvin speed decides how fast a magnetic disturbance travels. Plasma beta, the ratio of particle pressure to magnetic pressure, decides how obedient the tail is. In low beta regions, fields rule, tails snap sharply. In high beta regions, particles blur the response. These aren't jargon for show. They explain why sometimes you see a crisp break, sometimes only ripples. Same storm, different stage conditions. Tail disconnections belong to ion tails, not dust. Dust tails are grains pushed by sunlight and gravity, not field lines. So when the ion tail breaks, the dust fan usually stays smooth. This is a gift to observers. On wide field photos, if you see a sharp gap in the blue ion strand, but the dust fan flows on, you've witnessed reconnection written in glowing ink. Solar maximum thickens the script. 3 main actors. 1. Shocks from coronal mass ejections, compressing and twisting fields. 2. Giant current sheets where polarity flips, forcing comet tails to realign. 3. Background turbulence, making some cuts ragged rather than clean. And here lies a debate. Bold modelers argue that with many comets near the ecliptic, their plasma and dust seeds may stir turbulence, increasing reconnection chances and shaping small-scale solar wind features. Data-driven groups counter. Most comet tail anomalies are subtle kinks, ripples, twists, and full disconnections need just right timing. Their view: the sun is the conductor. Comets wave the flag, but don't drive the wind. I stand between. Models remind us that space is a sensitive, magnetized fluid. Obstacles matter. Data remind us that a clean break needs the right direction, time, and place. For practical US observers, this means one modest forecast. Between late October and mid-November, your odds of catching a disconnection are better thanks to comet crowding and storm rhythm. Most nights, though, you'll see only gentle bending, a prize in itself. Turning debate into experience is simple. Each time a coronagraph frame hints at a cut, log the time. Then rewind 2 or 3 days in solar reports. Was there a CME? What polarity? What speed? If it lines up, you've built a causal bridge. If not, you've learned that turbulence or geometry misled you. Both outcomes are lessons, not failures. Direct outdoor observing. Grand disconnections are rare to the naked eye. They happen near glare, but 2 tricks help. 1. After coronagraphs record a break, check the comet in dark skies a few nights later. The fresh ion tail may appear straighter, sharper for days visible in binoculars. 2. Use rapid, short exposures stacked, not long single frames. Ion tails hide better in stacks of quick frames than in a washed-out long shot. A private thought I'll share. A tail disconnection is one of the rare times you watch magnetic energy turn into motion before your eyes. It's like watching the wind change on a lake surface, ripples running with the shift. Each time, I feel lighter, not because the mystery vanishes, but because it speaks in a language we can learn. Solar maximum makes that voice louder. If you listen, this year's sky will feel both familiar and new, physics speaking in light. Next, we'll fold this plasma map into a concrete observing calendar for the United States, matching storm forecasts with comet positions to maximize chances of tail drama while staying safe and practical. We now have a plasma map. Let's fold it into a pocket guide for porches and backyards across the US. The goal isn't to memorize numbers, but to set rhythm. Each night, check the sun's pulse, match it with comet positions, choose a window, and record what you see. When many do this, one beautiful season becomes a living dataset. Start in late October. Pre-dawn around the 21st belongs to Swan. In the continental US, the East and Midwest get darker skies before sunrise, while mountain and western states enjoy dry air. Wake an hour before dawn. In the Northeast, find a clear southeast horizon. In the Midwest, wide plains help. Binoculars 10 by 50 suffice. Expect a fuzzy head, a short tail stretching a few degrees in dark, clear air. This is Swan at close approach, timed with likely solar activity. If a major CME erupted 2 or 3 days earlier, shoot sequences of short exposures to test for ion tail quirks. Keep ISO and aperture steady. Expose for 5 to 8 seconds. Repeat dozens of times. Even if no cut appears, your sequence may reveal subtle breathing with the wind. Meanwhile, 3-eye Atlas hides behind the sun. That makes daytime your shift. Coronagraphs update late night through pre-dawn local time. Drop in a few times, screenshot frames, mark times. It's like a light watch duty. You don't camp, you just check. If a cut occurs, your timestamp lands within minutes, good enough to link to solar reports later. Next, late October into early November brings Atlas K1 near the sun. Safety first, no optics near sunrise. By day, coronagraph feeds are your window, hunt signs, gaps near the head, ripples along the ion line. By evening twilight, if elongation grows enough, try wide field photos, 50 to 85 millimeters, toward west-southwest. The west and southwest US have dry horizons. The southeast should wait for cool north winds. Always timestamp. Compare your photos with same-day coronagraphs. You'll see connections between solar storms and comet tails. Early to mid-November. Lemon enters evenings, perhaps visible even to the naked eye from dark sites. The Midwest and the Northeast enjoy cold, steady skies. The Pacific Northwest must pick rare dry nights. Look southwest 45 to 60 minutes after sunset. A lemon may show a short tail in binoculars. If forecasts mention a CME 2 to 3 days earlier, upgrade your plan. Take sequences. Stack short frames. Highlight the ion tail. If skies are calm, study the dust tail's curve, practice reading sunlight's pressure. Keep a nightly ritual. Check 3 things before stepping outside. First, geomagnetic activity index quiet or active. Second, solar wind speed fast with favorable polarity means better tail odds. Third, moon phase. Bright moon, favor binoculars and coronagraphs. Dark moon, favor wide field photos. Geography shapes opportunities. In Alaska, combine auroras and comet watching. One lens for auroras, one pair of binoculars for low comets. Hawaii offers clear, steady nights ideal for faint ion tails. High plateaus in Colorado and New Mexico offer dry, low horizons perfect for lemon and K1. The mid-Atlantic states can wait for continental air after fronts cleaner skies. Urban dwellers, don't quit. Your dark sight is your screen. Coronagraphs need no stars overhead. Every time-stamped frame counts. To maximize tail cuts, follow a 3-day rhythm. When a CME launches, mark 2 to 4 days later as a tail window. Adjust by solar wind speed. Within that window, drop by the coronagraph feeds a few times. If nothing, you've lost minutes. If something, you've caught a cosmic switch flip. Add a teaching layer. Once a week, hold a family compare night print. 2 comet images days apart. At the kitchen table, ask, is the tail longer or shorter? Is the head brighter or dimmer? Is the dust fan more curved? Each answer unlocks a concept. Tail length equals wind. Head brightness equals outgassing and phase angle. Dust curve equals radiation pressure. Suddenly, the sky shifts from pretty to alive. And don't skip your logbook. Note, date, time, place, weather, gear, settings, and results. Add a line for feelings. Tonight, northeast wind, tail fluttered slightly, is worth more than a folder of unlabeled shots. By season's end, your log becomes your personal sky story. Share logs across states, and a collective picture forms, citizen science at work. My advice when writing this calendar, simplify ambition. Don't chase all in one night. Pick one comet, one goal. Today, Swan at dawn. Tomorrow, Atlas K1 on coronagraphs. Weekend, lemon after dusk. Small goals stack into a complete season. If clouds steal a night, take it as an invitation indoors. Reread notes. Study solar physics. Prepare to look deeper next time. From this calendar, the next step flows naturally, turning evidence into fair debate. With images, times, and causal bridges, we'll be ready to weigh big ideas with respect for wonder. In the next section, you and I will weave the threads, test science against speculation, and uncover what this once-in-a-lifetime season really means. You and I have built a calendar. We know when to look up and when to check screens. Now let's turn sideways to Earth itself, where those slender blue comet tails sometimes line up with warning lights on our infrastructure. I want to clear a common knot. 7 comets and 1 interstellar visitor are not causing geomagnetic storms. They don't flip switches on power lines or tap satellites on the shoulder. The real agent is the sun, through radiation and plasma winds. Timing overlaps temp stories, but our work is to separate coincidence from cause. Start with satellites because America's modern sky lives heavily in orbit. Solar storms bring 2 main problems. First, surface charging and particle hits that confuse electronics. High-energy electrons build up on a satellite's skin and arc between components, creating glitches. Energetic protons punch into memory chips. Flipping a single bit 0 becomes 1. Second, atmospheric drag. Storms heat and puff up the upper atmosphere, like a thicker coat that the satellite must push through. Low-orbit satellites slow down, needing fuel burns to reboost, or risk falling early. Next comes GPS. Every phone, plane and tractor trusts it, but GPS is a radio moving through the ionosphere. Storms make that layer ripple, signals twinkle, a phenomenon experts call scintillation. In Alaska, or across the equatorial belt from South Texas to the Caribbean, stormy nights can swell errors. Airlines on polar routes may adjust course or altitude to avoid blackout zones. For you and me, the lesson is simple. Don't lean on GPS alone if you must be somewhere exact during a storm alert. A paper map or downloaded offline map is your quiet insurance. Radio and telecom feel storms differently. Major events cause radio blackouts on certain bands, leaving long-range marine or aviation comms patchy for hours. Fiber optic ground networks mostly shrug, but their timing systems often rely on GPS clocks. Those need backup to stay in sync. Knowing this helps you read news calmly. When a headline says outages, you'll know where to look for the root cause. The power grid is where fears inflate most. Strong storms can drive stray currents through long transmission lines, saturating transformer cores, heating them, shaking them, and even tripping breakers. Quebec's 1989 blackout is the go-to cautionary tale. In the US, operators now watch geomagnetically induced currents and can reconfigure or shed load. For citizens, the practical prep isn't hoarding canned beans because of comets. It's simpler. Keep a flashlight, a charged backup battery, and glance at space weather alerts the way you'd check a rain radar. So what role do comets play? They are wind flags. Ion tails are instant maps of solar wind direction and field orientation. When you and I see a tail cut on coronagraph frames, we know a magnetic twist or impact just passed there. But does that same twist strike Earth? Not necessarily. Solar wind spirals like a coiled spring. A shock can slam a comet to the right of Earth and miss us entirely to the left. That's why tail cuts are data points, not doomsday omens. Like spotting thunderheads to the west, you note them, but you wait to see if the wind blows them your way. To read alerts in plain English, use the scales American agencies publish. G for geomagnetic storms, G1, minor, to G5, severe. R for radio blackouts, R1 to R5. S for solar radiation storms, S1 to S5. If you see a G2 or G3 alert with favorable polarity, expect auroras and some GPS wobble. An R3 means don't be surprised if HF radio fades. These scales are our shared dictionary using them. You and I speak the same language as grid managers and satellite crews. I've learned one key mental habit: tiered expectations. For satellites, expect plenty of hiccups. A few disasters engineers design backups. For civilian GPS, expect temporary errors at high latitudes or equator zones, but not collapse. For the grid, expect operator adjustments far more often than blackouts. And above all, expect social media fireworks every time a comet tail breaks. Stories that love drama more than mechanism. You and I, by knowing the mechanism, can add context instead of panic. Turn comet watching nights into STEM lessons at home. When a coronagraph shows a tail disconnection, open a space weather dashboard beside it. Ask your child, if that shock travels Earth's way, how long? If it misses, what tells us so? I've seen evenings like this ignite curiosity better than any classroom. And more than that, they build a mindset. First ask, what mechanism? Then what evidence? Then what consequence? My personal take, this season is both dazzling and noisy. Dazzling because rarely do we see so many wind flags at once. Noisy because media ecosystems prize the thrilling story. I don't want you to hide in a bunker, nor drift sky drunk without looking at dashboards. Between those poles is a simple path. Understand solar storms like weather, trust professionals tending grids and satellites, and keep a small notebook. Write down tail breaks, log nights when the radio hummed oddly. Those pages will steady you more than rumors ever could. In the next part, we'll turn further practical drafting a preparedness notebook for individuals, families, classrooms, and industries so that a comet-rich, storm-loud season becomes not a crisis, but an upgrade in resilience. In the last part, you and I separated beauty above from risk below. Now let's turn that understanding into a small preparedness handbook, practical, calm, and easy to carry into daily life. The goal isn't to script a doomsday movie. It's to set habits that let you still watch comets, still make it to work on time, still tell the kids science stories without stress. Think of it as 4 layers: individual, Family, community, and profession. Individual layer. Start with information. Each morning, check 2 things as casually as you check the weather app. 1. The geomagnetic storm index, G1 to G5. 2. Solar wind speed and polarity. If today looks unsettled, you don't cancel plans, you simply pack a backup. Download an offline map for your city. Scribble a basic route on paper if you're heading somewhere new. Slip a flashlight and a phone power bank in your bag. That's it. Not stockpiles, just small anchors against inconvenience. Family layer. Keep rhythm steady and make the sky a lesson. Pick one family night each week. Open the live coronagraph feed. Point out a comet tail quivering and ask the kids to guess how long that ripple might take to reach Earth. Then go outside. Show them Jupiter or a faint comet through binoculars. If you can, snap a phone photo on a tripod and teach them the difference between a dust tail, curved, and an ion tail, straight. Each story adds vocabulary, solar wind, magnetic field, and steals power from rumors. In the house, check the basics as if for winter storms, working flashlights, spare batteries, and smoke alarms with fresh cells. Simple, routine, reassuring, community layer. This is where schools, libraries, and astronomy clubs shine. Imagine a local library hosting a comet night. One station watches live solar images, noting times when a tail cuts or ripples. Another station outside shows visitors how to spot a faint object near the southwest horizon. A third lets kids cut paper to model dust versus ion tails, learning why one bends and the other doesn't. Tape the latest comet photo beside a solar wind graph on the wall. After a few weeks, you've built a living timeline. In schools, a teacher can run a 3-day project. Day 1, draw tail directions on comet photos. Day 2, mark solar eruptions on a timeline. Day 3, compare predictions with real disconnections. No grades needed, just practice in asking mechanism first, evidence second, consequence third. Professional layer. Pilots, network engineers, power operators, each has tailored playbooks, but our shared thread is anticipation. For polar airline routes, the key is awareness of radio blackout alerts. A minor reroute beats flying blind. For IT teams, it's about GPS clock dependence, check your backup time sources, run a drill. For grid operators, it's monitoring induced currents and shedding load briefly if needed. Citizens don't manage those levers, but we can support by reducing unnecessary power draw during alerts and by spreading accurate explanations instead of fear. Amateur radio groups deserve a mention too. Their ears often catch storm effects before official dashboards do. Invite them into public events. They can show kids how voices fade and return as the ionosphere flexes. When to stop outdoor viewing? It's simpler than you think. Radiation storms, the S scale, matter for pilots and satellites, not people on the ground. Geomagnetic storms, the G scale, matter for power lines, not your backyard health. The real stop signal is local. Clouds, thunderstorms, or kids' bedtime. Don't sacrifice rest or safety. The comets will write their stories again tomorrow. And finally, a soft layer, attitude. We humans love the extraordinary, but often forget the ordinary. Yet resilience is built from ordinary rituals. Glance at the space weather index, the way you check the rain forecast. Keep a flashlight charged. Log comet tail breaks in a notebook. Tell your child why one comet tail bends while another runs straight. None of this is dramatic, but by season's end, it weaves a quiet confidence you understand the sky enough not to be swayed by hype, and you respect Earth systems enough to trust their guardians. My personal conclusion is one sentence. The best preparedness is to turn a rare season into a shared class. When communities learn together, big questions lose their sharp edges, and the sky returns to its proper role, a patient teacher. You and I have talked about plasma, ion tails, and measurement scales. Now we step into another realm just as important, the realm of stories. Because every time the sky grows busy, Earth below grows busy too, not only in its infrastructure, but in human imagination. Comets have long carried names of omen, a broom sweeping away dynasties, a herald of change. Today, the same glowing streak carries hashtags and headlines. I want us to face this, not to dismiss feelings, but to understand the mechanism that makes us love, fear, and sometimes misread the sky. History gives us a softer entry. People always lived with the sky as with the sea. When the sea changed color, fishermen changed their habits. When a comet appeared, people linked it with events on Earth, simply because the two came close in time. A war once began during a comet's bright season. A plague once coincided with a trailing tail. Our brains dislike randomness. They are machines built to connect dots. Chroniclers wrote those pairings down as couplets. Comet and change, omen and fate. Centuries of repetition turned them into tradition. That habit hasn't vanished. It's just moved pages. Today, during comet season, you see videos online. Weather clips, tech glitches, then a comet tail spliced in. Dramatic music, bold text. For a moment, you feel someone knocking from the sky. That feeling is natural. The problem comes when feeling outrun by questions. You and I don't need to smother feelings. We only need to invite two other guests into the room: mechanism and repeated evidence. Mechanism first. How could a comet cause a geomagnetic storm? We've answered, it can't. No wires run from its tail to Earth's grid. No finger snap jolts satellites. What can happen is that its ion tail snaps under solar wind. That's an effect. The cause lies in the sun. Once the mechanism is clear, many stories fall away. Storytellers need a physical bridge. Without it, only the feeling remains. Repeated evidence is the second guest. With 7 comets this year, you have plenty of chances to test. Suppose someone claims every tail break means a radio outage. You check your log. Break 1 was there. Break 2, no. Break 3, maybe. When results mix, the strong claim must soften into a conditional one. Sometimes when solar wind hits Earth, effects overlap. This lesson is bigger than astronomy. It's a way of living slower, resisting urgent words. Our brains have habits that make omens easy to see in coincidence. First is attention bias. The unusual sticks stronger than the everyday. With 7 comets above, every oddity below seems louder. Second is availability bias. You just watched a tail break video. The next day, GPS stutters. You link them by reflex. Third is narrative bias. Humans weave fragments into stories. Stories soothe, but they don't always honor data. I won't tell you to drop stories. I suggest a small habit. Whenever you're about to say because, try layering it 3 ways. First layer, plain event. I saw the tail break at this time. Second, near inference. Maybe a solar plasma cloud passed there. Third, narrative. The sky feels busy, like it's speaking. When you separate the layers loudly, you give listeners a map. They know which floor you're standing on and can climb with you when new data arrives. For classrooms, this comet season is perfect for teaching critical thinking with wonder intact. A teacher could stage an investigation. Group A hunts tail breaks in images. Group B checks solar wind reports. Group C looks at tech news from the same day. By the end, 3 timelines are on the board. Which lines cross? Which just run parallel? When students draw those lines themselves, they learn not to force overlaps just for narrative neatness. That skill may be the most precious gift the sky gives a class. For you and me, adults who like to watch and think, a small ritual can hold balance. Call it the 3 boxes. Box 1, confirmed fact. Box 2, current inference. Box 3, open story. When you watch a bold video, sort its claims. If it's all box 3, with no box 1, you know to smile and scroll on. If it's rich in box 1, with some box 2, you know it's worth your time. The The boxes are simple, but they help us walk through a noisy season calmly. My opinion on omens is simple. People need stories like they need salt. A good story is not flawless truth. It leaves room for evidence to enter and an exit door for revision. Comets are a perfect stage for that kind of story. When you stand under the night sky and watch a faint streak drift, your heart has every right to tremble. Then you open your notebook, write the time, the direction, and tomorrow you check solar data. Feeling and discipline travel together. The sky deserves to be loved that way. In the next part, you and I will face modern amplifiers, social media algorithms, click-hungry headlines, and how to keep science from being swallowed by hype, while also learning how to tell beautiful stories without betraying data. You and I just opened the old chest of omens. Now let's open a much newer one. Algorithms. No incense smoke here, just lines of code deciding what makes people stop scrolling. And comets. They're irresistible food for those lines of code. A dark sky, a glowing tail, a few bold captions, and the video soars. I don't blame the algorithm. It does what it's built to do. Maximize attention. The problem arises when attention replaces evidence. Our job, if we want to love the sky without losing our minds, is to walk between two lanes, harnessing that reach to tell stories well, while keeping a rope tied firmly to data. Let's talk headlines first. A good headline invites viewers in. It doesn't lock them in a conclusion. A bad one judges, declares, and insists on a because before the viewer hears a single mechanism. You know the type. 7 comets bringing storms to Earth. Interstellar commander controls the tails. Lines like these make people hold their breath, but cut off the path back when evidence shifts. I prefer open headlines. NASA on alert doesn't scream catastrophe. It signals rising pulse because of a rare season ahead. New company doesn't imply conspiracy. It simply states that 3i Atlas isn't alone in the sky. That phrasing lets us step into the story with curiosity instead of fear. Now, algorithms. They love 3 things: novelty, strangeness, and strong emotion. The good news is that science has all 3, if told right. Novelty is in the solar storms and sudden tail breaks. Strangeness is in 3i Atlas's chemistry sea. 2 speaking before water. Emotion is in the sight of a comet's tail snapping like a plucked string. What we don't need are invisible wires tying wrong things together. I often use a simple frame when writing: story, mechanism, evidence, uncertainty. 4 legs of a chair. Break 1, and the chair wobbles. Keep all 4, and you can sit comfortably for a long time. We also need a language of humility. Instead of declaring, we use verbs that leave windows open. Data suggest, spectra show, images record, models predict. Not because we fear blame, but because we respect how knowledge grows. This season, images, light curves, and wind charts will constantly update each other. Tonight's conclusion may need a tweak tomorrow. Speaking this way invites people to travel with us, not bow to a fixed prophecy. Some creators worry. If we speak cautiously, will algorithms ignore us? The honest answer: sometimes yes, sometimes no. But caution isn't boring. You can still build bridges of authentic feeling. Share the moment you sat at a screen, saw a thin gap near a comet's head, and felt your heart skip because you knew you were watching magnetic energy turn into motion. Share the night you stepped outside with binoculars. Clouds ruined the view, yet a coronagraph image delivered beauty at the same time. That emotion isn't bait. It's an invitation into real life, where science brushes skin. Viewers in the United States need shortcuts so they don't drown in noise. A simple sketch of dust tail versus ion tail, a 3-day window from solar eruption to Earth impact. The GRS scale is explained in 1 line each. Repeat these often, like weather maps in a forecast. Algorithms reward repeated patterns with variation. Science works the same way. Each time you repeat a concept with a fresh example, you lay another brick in memory. To fellow sky storytellers, I'll say this. Don't fear the words I don't know. They don't weaken your work, they deepen trust. Don't hesitate to drop a link to public data. It won't make viewers leave, it will make them return. Don't skip the 10 seconds it takes to sketch solar wind with your hand, even if your AI voice is velvet smooth. A hand-drawn doodle is a crutch for memory, and when you err, correct quickly and openly. The algorithm may ding you for a day, but collective memory will reward you far longer. For viewers, one small habit protects peace of mind. Ring the bell for a few channels that tell science slowly, then treat fast videos like dessert, not the main meal. When you see a headline too certain, scan the description. Does it cite data? Note observation times? Admit uncertainty? 3 quick checks are like trail markers in a forest. If present, you keep walking. If absent, you slow down. I want you to see something hopeful too. Algorithms don't just amplify fear, they also amplify wonder. A time-lapse of a comet's tail break, explained clearly, can travel just as far as a conspiracy if the teller wraps it with rhythm, music, and pauses that let viewers breathe. This season is a chance for small channels, local libraries, and amateur clubs to prove that slow stories have strength. You don't compete by shouting louder. You compete by offering steadier eyes. My opinion is simple. We can't, and don't need to, algorithms. But we can fix how we receive and how we tell. If every storyteller paused a beat before saying, because, and every listener opened one data tab before sharing, the sky would be quieter without being duller. I want this season of 7 comets and 1 interstellar guest to stand as a first example of responsible science storytelling, serious but still inspired. When you and I speak in the shared language of data, every kind of story has a place. You and I have journeyed far from ion tales to solar storm calendars. Now we step into the most dramatic territory. What if 3i Atlas were a probe? The question has weight because it gathers 3 feelings into one: rarity, coincidence, and mystery. But to keep the question from swallowing reason, we need a proper operating table. On that table, each scalpel is a measurement. We don't stab, we touch lightly and ask, if it were a probe, what evidence must exist? If it were natural, what signs should appear? A small trick I use when doing this exercise is to make a promise. We'll gladly change our minds when evidence invites us. Step 1. Trajectory and thrust. An artificial craft doesn't just drift. It controls its orientation and sometimes changes velocity. In astronomy, the most common push comes from gas jets as ice sublimates. That force points roughly sunward and scales with sunlight. So if it were a craft, what should we look for? We'd look for acceleration against the sun's direction without a brightness spike from new outgassing. We'd look for small position shifts away from standard non-gravitational models, repeating in patterns more like code than weather. In practice, astronomers fit all observations to 3 non-gravitational parameters: radial, transverse, and normal to the orbital plane. If those vary in a rhythm disconnected from sunlight, the question mark grows. But if they track sunlight the way comets normally do, our first scalpel says, most likely natural. Step 2. Material signatures. A genuine craft would carry substances we don't expect in an icy nucleus, sharp metallic reflection lines, odd absorption bands, or heat curves carrying excess energy beyond sunlight. The educational takeaway here is simple. Dust and ice give reddish, featureless spectra. Gases produce bright emission bands of simple molecules. Metals flash mirror-like glints. Engineered composites leave strange slopes and unusual polarization. If observers report repeating mirror-like flares or narrow emission bands not in comet libraries, that's a yellow light. If instead the data keeps showing dust, ice, and a coma dominated by CO2 over water, with polarization typical of fine grains, our second scalpel leans natural. Step 3. Spin and orientation. Natural objects tumble like lumpy rocks, light curves wobbling slightly, sometimes shifting with jet activity. Artificial craft may hold orientation or adjust it on schedule. Which observations help us distinguish? Light curves. If brightness varies steadily over many nights, we can measure a rotation period. If that period changes exactly when geometry favors communication or shifts too fast without new outbursts, explanations get tough for a natural origin. But if brightness patterns wax and wane in step with solar angle or gas jets, then we're reading a weather log, not a pilot's diary. Step 4. Voices on the airwaves. If it were a craft, there might be signals. The easiest to catch wouldn't be a cosmic speech, but a narrow line in radio or optical bands, sliding gently in frequency with orbital Doppler shift. This brings in another concept, the waterfall plot, showing frequency over time. Artificial signals are narrow, persistent, and drift smoothly with motion. Scientists habitually aim big antennas during close passes, recording every narrow trace and removing known Earth interference. If nothing remains but ordinary noise, our scalpel says, silence is still data. It doesn't disprove craft, but it shrinks the box of possibilities. Step 5. Tails and plasma. A spacecraft doesn't need a tail. If it had one, it would be an extravagant disguise. Real comets love to tell tales with theirs, bending with solar wind, snapping under magnetic reconnection, fading near glare. If 3E Atlas shows an ion tail reacting exactly to wind, a dust tail curved by sunlight, and a near-nucleus gap matching plasma events, then either the universe is staging flawless theatre, or physics is simply doing its job. You may ask, could a hyper-advanced craft fake all natural signs? On paper, yes. In practice, cost and motive matter. Why carry a factory of dust and gas just to fool a species that would happily be convinced by a single radio ping? This isn't to close the door on imagination, but to remind us that science also weighs the efficiency of hypotheses. At this point, we hold two baskets. Basket A, required artificial signs, non-solar acceleration, anomalous spectra, regular mirror flares, consistent narrow signals. Basket B, natural signs, solar-driven acceleration, dusty icy spectra, wind-shaped tails, radio silence. We drop each piece of data into one basket or the other. When basket A fills, we change tone. When basket B fills, we smile at a strange but natural visitor. Observers in the United States play no small role. You can contribute light curves with accurate timestamps to help measure rotation. You can shoot short exposure sequences to track ion tail length before and after solar events. If you dabble in software-defined radio, you can scan small frequency windows during the pass, uploading narrow odd traces with time and pointing info. Citizen science here isn't a mystical treasure hunt. It's hundreds of eyes and ears logging carefully, ready to speak when the moment comes. And my own stance, you know by now. I stand at the crossroads, leaning toward natural, because every scalpel so far points that way, yet I keep a chair open for surprise. If tomorrow someone reports a drifting narrowband signal, or next week position data reveal a sunward push without brightening, you and I will joyfully clear space for a new story. Until then, the beauty of the probe hypothesis isn't the conclusion, but the lesson in how we test it, with patience and the right tools. In the next section, we'll step into even darker territory. Apocalyptic scenarios and invasion stories dressed in comet tales. We'll listen, slice them apart, and see where those fears fall when exposed to the light of probability and mechanism. You and I have dissected the probe idea. Now we walk into the loudest hallway, apocalyptic scenarios and invasions hidden in comet form. These stories grip us because they tie together three chords at once: survival threat, deliberate malice, and urgency. When 7 comets appear alongside one interstellar visitor, the imagination easily drags us toward the cliff's edge. But every cliff also has steps leading down, not just a plunge. Our steps are two words: probability and mechanism. I'll walk them with you, not with hollow reassurance, but with questions that force fear to answer. Step 1. Impact. If a comet were truly on course to strike Earth within months, what are the mandatory signs? 1. Its orbit must intersect Earth's orbit at the exact time Earth is there. 2. As more data arrive, uncertainties must shrink toward collision, not drift away. 3. The geometry phase angle, angular speed, sky path must match a rendezvous, not a flyby. Astronomy here is like a train track. If the car is heading to the station, every position measurement converges on that station. If not, we're just watching a passing train. You've seen headlines, passing close to Earth, just tens of millions of kilometers away. That phrase, just tens of millions, makes the heart race. But in space, tens of millions of kilometers is freeway distance, not a guardrail scrape. This is a chance to teach a unit, the astronomical unit, the Earth-Sun distance. If a comet's closest approach is a quarter of that, it's still dozens of times farther than the Moon. Earth's gravity at that distance is too weak to reel it in unless geometry already sets the crash course. And if that were the case, months of data would have screamed long ago. Without that convergence, impact talk is magazine fiction. Step 2. Bundled events. 7 comets, a solar maximum, some tail disconnections, a regional outage somewhere. It feels natural to string them into one chord and call it a sign. But statistics teach a simpler lesson. Rare events bundled together look like destiny, while each on its own still follows its own cause. The way to untangle is to put each event back on its axis. Outages belong to R, radio. Auroras belong to G, geomagnetic. Radiation impacts flights under S. Tail breaks belong to local solar wind at the comet's position, not Earth's. Once you reassign them correctly, the sine cord unravels into smaller strands, each telling a clear story. Step 3. Invasion in disguise. Here's where modern imagination fuses with unease about advanced technology. If a civilization could direct 7 giant bodies and dress them up as comets, the first question is, why bother with a disguise? Disguise means the deceived party has the power to resist if they knew. Humanity today cannot stop an interstellar fleet, even if it arrived unmasked. So what's the strategic gain in building a colossal masquerade? This isn't just philosophy, it's Occam's razor. When a theory requires far more assumptions than needed, caution is mandatory. Step 4. Signatures that cannot hide. No matter how clever the disguise, 3 things are nearly impossible to conceal. First, orbital logic. You can mimic non-gravitational thrust with jets, but jets leave light, dust, and gas spectra. If outgassing is constant, yet no brightening or gas lines appear, the act slips. Second, time. A fake comet must keep its rotation and jets consistent across weeks, angles, and distances. Small inconsistencies add up in light curves and tail shape. Third, communication. Coordinating 7 objects across a vast space without any structured signal in radio or optical is either impossible or pointless. One can say, they use channels we don't know, but that adds assumptions to dodge tests, not to make predictions. Step 5. Strategic logic. Suppose an invasion were real. The rational strategy would target Earth's weaknesses on the ground or in near-Earth space. Using comets as weapons is clumsy, high risk, and unreliable. Since geometry and physics dominate outcomes, a civilization capable of interstellar travel has access to tools far subtler and more effective. So why pick the noisiest, least controllable method? When a theory makes attackers act irrationally, the theory weakens, not because we're optimists, but because we respect basic logic. Step 6. Systemic collapse. Some may say, fine, no impact, no invasion, but what about systems breaking down? This is the only area worth soft vigilance, but the right vigilance points to the sun, not the comets. Strong geomagnetic storms can force grid adjustments, GPS shifts, or flight reroutes. These require operational checklists, not supernatural scripts. Beyond logic, let's visit emotion. Fear is useful when it keeps us from the cliff, harmful when it makes us turn away from the sky. This season, you'll see quick cuts, low voices, dense captions. You'll also see real tail breaks and calm nights with binoculars. You get to choose the main course. Mine are the small aha moments. A slim gap in an ion tail, matching a solar wind switch. A light curve of 3i Atlas wobbling just like a natural rotation. An amateur radio report of a silent band right when R-scale climbs. These build scaffolding where fear has no room to balloon. Here's a classroom exercise. The 5 gates. When you hear an apocalypse claim, check the gates in order. Gate 1, orbit. Gate 2, position convergence. Gate 3, spectra and brightness. Do they fit real outgassing? Gate 4, signals any structured narrowband. Gate 5, strategy, does it make sense? The fewer gates a claim passes, the quicker you smile and move on. If it clears more than usual, you pause, check sources, and wait for independent teams. This turns fear into process, and process is the best sedative. My personal view ends with a simple picture. I see this season like a freight train passing a town at night. The horn blows, lights sweep, the town wakes and talks. Some cry robbery, some doom. Most stand by the tracks, count cars, log times, and show children why wheels spark under strain. The train passes. In our notebooks, 7 comets, 1 interstellar visitor, many lessons in wind and tails, and a warm night on the porch. If there's something to fear, it's only the chance we forget to write those lessons down because we were too busy listening to shouting. Don't let that happen. In the next section, we'll step away from extremes and return to the center, how science sets evidence standards, how debate keeps fairness, and how to balance wonder with discipline when retelling this rare season to one another. You and I have walked through the fog of dramatic hypotheses. Now we return to the center, where science pitches its tent, the measure of evidence. I do not want to turn this part into a dry lecture. I want you to see it as a toolbox you carry out to the porch each night, next to your binoculars and folding chair. The goal is this: to keep the wow when a tail breaks, but still have the right tools to know whether what you just saw is a signal or evidence. I begin with a simple 4-legged frame that you and I can use to make debates less slippery: geometry, photometry, spectroscopy, and radioplasma correlation. Geometry answers the question, where and when. Photometry, or brightness over time, answers rhythm and intensity. Spectroscopy answers what it is. Radioplasma answers what the environment has done to it. A strong claim needs at least 2 solid legs, preferably 3. If it stands on only one, no matter how striking, we call it a working hypothesis, not a conclusion. The first leg is geometry. You and I have used it many times without naming it. When you record the time of a tail break on coronagraph images, you are setting a geometric marker. When you draw the comet's position relative to the sun, you are establishing context. At a higher level, geometry demands something else: error margins. Without them, every arrow on the page looks more precise than reality. In your logbook, try writing approximate, or plus or minus a few minutes and plus or minus a few degrees. You are not weakening the data by admitting uncertainty. You are giving others the key to align their data with yours. The second leg is photometry. The light curve is a comet's heartbeat. It tells of the weather on the nucleus, outgassing more or less, spinning fast or slow, and whether a dark patch has turned to face the sun. One small principle to avoid phantom rhythms. Longer sequences outweigh short ones. 3 nights spread out are better than 1 perfect night. Another point: keep capture settings consistent so relative brightness has meaning. When you place the light curve next to the solar wind chart, do not rush to say because. Look first. Do the brightness peaks really fall after strong solar wind bursts with the same delay each time? If yes, that is a thread. If not, then there are two parallel stories, both worth keeping. The third leg is spectroscopy. Each emission band is a letter. Together, they form words. At home on the porch, you and I cannot reach high spectral resolution, but we can still learn the language at a broad level. An ion tail is straight and blue. A dust tail is curved and warm white. The head glows yellow-green when gases increase. When you read the work of professional groups, note two things. Do they say detected or suggested? And do they normalize for distance and phase angle? Those phrases are signs of discipline. And when someone boasts of a strange feature without showing a comparison spectrum, you know to place it in the box of speculation and wait for confirmation. The fourth leg is radioplasma. This is the bridge between the sky you see and the space weather you cannot see. The measure here is not only yes or no, but also time delay. A tailbreak near the sun does not mean your home will have a storm that night. If multiple events, tailbreaks, CAPE increases, radio blackouts, repeat with the same delay consistent with solar wind speed, then we have a causal network. If not, we have a choir singing different parts. From these four legs, I draw a 5-rung ladder of evidence that you and I can agree on, to use in conversation with each other and with the community. Rung 1, a single observation, no repeat. For example, one night the tail trembles. Conclusion, record it, do not speculate. Rung 2, internal repeat. Several nights, same setup, the same trembling rhythm. Conclusion, propose a light hypothesis, such as possibly linked to solar wind. Rung 3, co-observation. Two people in different places see the same feature at nearly the same time. Conclusion, raise the hypothesis, invite comparison with space data. Rung 4, cross-discipline support. Add spectroscopy suggesting composition or plasma indicators showing a magnetic shift at the right moment. Conclusion, write confidently. Evidence consistent with. Rung 5, replication and independent critique. A different group with different data reaches the same conclusion, and criticism finds no major errors. Conclusion, treat as solid for now, ready to update with new data. I know you like pocket tools. Here is another, the triangle of 3 easy mistakes. First mistake, choosing samples after looking at the data, the so-called p-hack by eye. You see 3 coincidences and declare a pattern, forgetting the times when nothing matched. The fix, define beforehand the time window you will count as coincident, for example, plus or minus 12 hours, before tallying. Second mistake, mixing reference frames. You compare coronagraph image times with local journal times, but forget to convert. The fix, always note UTC with local time. Third mistake, ignoring uncertainty. Saying brightness increased without knowing if it rose beyond the margin of error. The fix, estimate rough error from the scatter of nearby frames. Now comes the persistent question, how strong is strong enough? For ordinary claims, you and I can be satisfied at rung 3 or 4. For extraordinary claims, there is coordination, there is an unknown agent. The ladder must reach rung 5 and even require extra independent checks. The phrase, extraordinary claims require extraordinary evidence, is not a moral slogan, it is an economy of knowledge. The further from the baseline model, the higher the cost of being wrong, so certainty must rise. One more practice, fair dialogue. When there is disagreement, try the principle of steel and cotton. Steel is when you restate the other side's argument in its strongest form, until they nod and say, yes, that is what I mean. Cotton is when you question the evidence, not the motive. You saw the tail break at 2:10 UTC. Does the frame show a timestamp? And what window did you use compared with the CME? Questions like that keep the debate on the field of data, not on personal ground. Let me tie this together with a simple example. Suppose tonight you see on coronagraph footage a gap near the head of Atlas K1's tail. Rung 1. You capture the frame. Note the UTC. Rung 2. You check frames before and after, making sure it is not a compression error. Rung 3. You search the observing forums to see if someone in another time zone saw it too. Rung 4. You look at solar wind charts, see a magnetic field shift crossing the comet's orbit at that same plus or minus 6-hour window. You write, evidence consistent with a tail break due to magnetic field shift. Rung 5. The next day, an independent team with higher resolution imagery confirms it and adds ion spectra. At that point, the story is full. You have your own measure, cross-check, and critique. My personal view is that intellectual kindness lies in that small act, writing sentences that fit the data you have, leaving a crack open for tomorrow. I believe this style does not dim the fire of wonder. On the contrary, it extends its flame across many seasons. When you and I stand under the sky, listening to a slow AI voice at night, the feeling of wow is real. The 4 legs and 5 rungs are simply a way to keep that wow from becoming oh, I was too quick. In the next part, we will move from the toolbox to a storytelling pact, a short handbook that anyone, from creators to teachers to parents, can use to tell the tale of the 7 comets in a way that is engaging yet fair, with formulas for openings, rhythms, and pauses tested right there on the porch. You and I now carry our toolbox of evidence. Next, let's sign a pact of storytelling, so whenever you write a video description, record narration, or stand in front of a class, the tale of 7 comets and 3 Atlas is both captivating and fair. Think of it as a short guide for the slow, steady voice, warm enough to soothe the evening, sharp enough to honor the data. The pact has 4 principles, 4 rhythms, and 4 tools. You can take whichever pieces fit your style and weave them into your script. Principle 1. Begin with a question, not a conclusion. Instead of declaring this is a sign, invite the listener to wonder with you. Start with a familiar image. Tonight, if you step onto a porch in Ohio or Arizona, you'll see a faint streak pulling your eyes. I wonder, what message is that tail writing on the wind? A question keeps the door open for evidence to walk in and gives the audience permission to explore alongside you. Principle 2. Anchor every claim to a measure. If you say brighter, note that the exposure settings were consistent. If you say close, translate into scale, many times farther than the moon. If you say rare, frame it with history. This hasn't happened in decades of observation. The story flows smoothly, but with anchors that keep it grounded. Principle 3. Uncertainty belongs inside the story. Don't hide it. Let it breathe. You can say, spectra suggests CO2 dominates, but the error bar is wide. I'll update when new data arrives. That doesn't bore the listener, it teaches them how to stand next to you, not across from you. Principle 4. Set emotion beside mechanism. Admit, my heart skipped when I saw the tail break. Then explain magnetic reconnection. People need both feeling to enter, mechanism to stay. Now the 4 rhythms for a sleep documentary segment. Rhythm 1. Invitation. A short, clear image. The sky is a dark cloth. On it, a fine thread stretches taut. Rhythm 2. Scene and tool. You and I call that thread an ion tail. It's combed by the solar wind, and tonight the wind is shifting. Rhythm 3. Core knowledge. When the field twists, lines wrap the comet, reconnect, and the old tail drifts away while a new one sprouts in the new direction. Rhythm 4. Gentle exit. If you see nothing unusual, don't regret it. The tail is still speaking, just in whispers. This pacing leaves space for breath and matches the calm cadence of AI narration. Then, the 4 tools. Tool 1. Double layer story. Everyday and cosmic. In Texas, the highway at night looks like a dust-tail car light swept by radiation. Tonight, the sun does the same to real dust. Tool 2. Verbs of physics. Instead of vague, mystical energy, use field twists, plasma compresses, lines break and reconnect. Verbs become background music, making the narration vivid without effects. Tool 3. The 4-word closing formula. Story, mechanism, evidence, uncertainty. Tonight's story is a tail break. The mechanism is magnetic reconnection. Evidence, 3 consecutive frames. Uncertainty, the wind speed is still fluctuating. Tool 4. Time bridge, end with a promise. Tomorrow, if coronagraphs show another ripple, we'll line it up with the G-index and see if Earth felt a nudge. This keeps viewers returning, not from fear, but from shared learning. Some don'ts. Don't drown in numbers when one will do. Don't lock with words like certain or impossible. Science prefers unlikely under known physics. Don't turn debate into morality plays. Another narrator isn't wrong. They may just be at a different rung of evidence. Your calmness is your trust signal. If you're a teacher, here's a 1-minute opening you can borrow. Tonight, 7 visitors cross our backyard sky. You don't need a big telescope. Just a folding chair, a clock, and a few questions. Why is one tail straight, another curved? How can a faint streak speak of winds millions of miles away? I'll walk you through from story to mechanism, from screen images to invisible plasma. And if there's something we don't know, I'll say we don't know. Because don't know is a promise to tomorrow's sky. If you're a creator, here's a midsection frame. Each entry should be 2 or 3 sentences. Observation. Swan's ion tail showed a narrow gap at 2:14 UTC. Mechanism. A magnetic field switch passed through. Evidence. 3 coronagraph frames, 5 minutes apart. Uncertainty. Wind speed estimates still vary. Repeat this rhythm for each comet. Repetition with variation helps viewers learn structure along with the science. If you're a parent, your closing frame needs only a question. If there were no wind, would a tail exist? That one thought can carry a child closer to physics than any worksheet. My personal view of science storytelling is this. Don't try to outgame the algorithm. Win by relationship. When listeners trust that you share only what you've seen and understood, they'll return even if the title isn't shouting doom. When children trust that I don't know is a promise, they'll fall asleep with questions and wake with joy. Our pact doesn't need ink. It's signed by habit. Each evening, one short segment, one anchor of data, one gap for uncertainty, one promise to meet again. In the next part, we'll weave every thread into one framework of meaning, what truly matters in this rare season, from science to education to calm reasoning, so that when the story ends, you and I still hold a compass that works for the long road. You and I have gone through most of the emotional and technical turns of the season of 7 comets, plus the demanding interstellar visitor 3I Atlas. At this point, I want to reset the frame of value in a very everyday sense. After watching, learning, and dialoguing, what do we actually carry with us? Not the big headlines, not the loud stories, but the tools that live long in the drawer of memory. I see 3 pillars holding this roof steady: science, education, and the compass of thinking. Each pillar has roots that run deep and branches that cast shade. The first pillar is science, not in the form of scattered gasps, but as a rare opportunity for comparison. Normally, we observe one comet and then wait many years to meet a similar object. This season, you and I have a whole cast to place side by side. Pan-stars, distant and muted. Swan, fast and close. Stereo, difficult to see from the ground but bright on the occulting disk camera. Atlas K1, hot in the radiation field. 3I Atlas, chemically strange. Lemon, friendly to the naked eye. NEAT, the baseline rhythm of a periodic guest. When many storytellers walk across the same stage, physics reveals horizontal rules. Every ion tail points straight away from the sun, but their length and recovery time after breaking depend on the gas composition. Every dust tail is curved, but the degree of curvature reflects the distribution of particle sizes and the light. Parallel comparisons like these help us avoid personalizing a single phenomenon, and that is the moment science matures. In that scientific pillar, 3-ice atlas is like a rear-view mirror pointing to an entirely different road. You and I can hardly travel to where it was born, but its chemical makeup and light curve allow us to see a slice of planetary chemistry not from our home. The value here does not lie in labeling it as strange, but in putting a dot on the map of knowledge. There are regions of ice where CO2 speaks before water. There are ways of fragmenting and outgassing that do not quite match what we are familiar with. That dot will serve as a standard for many later models, even models not directly related to comets, such as the formation of early atmospheres or the origins of simple organic molecules in nebular clouds. The second pillar is education, in the broad and the near sense. Broad, because it reaches schools, libraries, clubs. Near, because it can live on your porch, between a folding chair and a clock. I think few subjects can change one's attitude towards science as quickly as the real sky. One evening spent recording the time of a broken tail and comparing it to the KP index the next morning holds more durable educational value than a test. For children, it is the first time they see invisible concepts truly bite into observation. For adults, it is the first time they see that a process of reasoning can be warm, slow, pressure-free, and still give intellectual pleasure. Education is also a lesson about community, a library setting up 3 stations, as we mentioned, a ham radio club sharing logs, and a group of amateur photographers standardizing timestamp labeling. When those small pieces fit together, they create a shared dataset that professional groups can use. The sense of contribution does not come from a medal, but from the moment you see your town's name in a thank you note at the end of a report. I believe such moments are what keep science tied to life, so that rare seasons are not just shows, but upgrades to the software of a whole town. The third pillar is the compass of thinking. If you ask me for one single question worth keeping long-term, I would choose this. Where am I standing among story, mechanism, evidence, and uncertainty? Just that one question, repeated enough times, will change the way you read news, talk, and decide. When a video says, a broken tail forecasts a storm, you immediately ask, is that story or mechanism? Is there a wind speed graph? Is there a UTC timestamp? Is there a physically reasonable lag window? When a friend asks, should we be worried? You don't reply with a gut feeling, but with the GRS 3-tier frame and a sentence like, tonight, there may be auroras, GPS error slightly higher, the grid may adjust operations, but there is no mechanism linking the comet directly to the grid. That compass does not make you dry. It only makes you fair with reality. The compass of thinking also saves us from a common trap, confusing meaningful coincidence with causation. In a busy season, so many parallel lines appear that they look like they cross. The compass reminds us that only when there is a clear mechanism bridge and a physically proper delay does an intersection become real. Otherwise, we simply let those beautiful parallel lines run alongside each other because each tells a story worth hearing. This may sound abstract, but it is very practical. It helps you avoid being pulled into the whirlpool of hot content while still enjoying the sky's beauty. I want to add another layer of value, small but precious, the rhythm of life. A season like this teaches us to slow down. You have to wait for clouds to clear, wait for the occulting camera to change frame, and wait for graphs to update. Waiting is a skill worn thin in the age of second-by-second updates. When we are forced to wait, the mind looks for ways to fill the gap, and the healthiest way is to ask questions. Why is the dust tail more curved than yesterday? Why does 3-eye atlas shine at times and be quiet at others? Those questions pull us away from the reflex to share instantly and toward the reflex to record, compare, and verify. Each night, just one question and one timestamp trains mental muscles you can still use next week next month. My personal opinion about the essence of value is this. A rare season does not leave behind a statue, it leaves behind a habit. If, after this season, you and I still check the storm index as we check the rain forecast, still keep an offline map on our phones, still teach children to separate story from mechanism, then 7 comets and 1 interstellar guest have done their finest work. They don't need to sweep away a dynasty or rewrite destiny. They only need to remind us that the vast universe can enter the small home through careful acts and a steady heartbeat. In the next section, I will gather the final threads into a small manifesto for sky lovers. 8 commitments you and I can read each time we begin a night of observation, to keep the magical flame lit without burning away discipline, and to ensure that our conversations with friends in America remain warm, clear, and fair. You and I have packed up the toolbox, adjusted the compass of thinking, and hung the coat ready on the porch. Before stepping into the final nights of the comet season, I want to invite you to sign a small manifesto, not a solemn document, but 8 commitments you can whisper to yourself before turning on the camera or opening the occulting disk stream. 8 short, easy to remember sentences, warm enough to keep the magical flame alive, steady enough not to slip on evidence. I will read each sentence, explain why it is worth reading, and point out a small practice to accompany it. Whichever sentence you nod to, carry it with you tonight. Commitment 1. I will begin with a question, not a conclusion. Each night can open with a simple question. Tonight, what is the wind saying to the ion tail? Questions slow the pace, encouraging you to observe before interpreting. The small practice is to write that question at the top of the notebook page, with UTC. When you return at the end of the night, try to answer with one line. It doesn't need to be complete, only true. Commitment 2. I will anchor every claim with a measure. If I say bright, I record the shooting conditions. If I say close, I convert it into familiar units, like a fraction of the Earth-Sun distance or multiples of the Moon's distance. The small practice is to standardize a note template, 3 fixed blanks, equipment and settings, position and time, relatable units. Repeat that template and you automatically keep a data anchor in your story. Commitment 3. I will respect uncertainty as part of truth. The sentence, I don't know yet, is a ticket to return tomorrow night. The small practice is to add an uncertainty line at the end of each note. For example, estimated wind speed fluctuating, no spectrum confirmed yet, time error of about a few minutes. That line makes your notebook resemble a laboratory, not a bulletin. Commitment 4. I will separate emotion from mechanism, then place them side by side. I allow myself to gasp when seeing a broken tail, then set beside it a calm description of magnetic reconnection. The small practice is to write twin sentences. Emotion opens the way, mechanism keeps the rhythm. Example, that moment kept me silent for a minute. The field lines just shifted and the old tail drifted away. Commitment 5. I will cross-check multiple sources before speaking strongly. 1 observation, 1 light curve, 1 plasma sign. 2 of 3 is good, 3 of 3 is solid. The small practice is to draw a 3-column checklist on paper. Geometry and photometry, spectrum and color, wind and magnetic indicators. Each finding you mark in the proper column. When 2 columns have marks, your words can move from maybe to consistent with. Commitment 6. I will restate the other person's argument in its strongest form before rebutting. This is the bridge that keeps the community standing on the same field. The small practice is to write a short paragraph beginning with, I understand you are saying that. Then record the idea exactly before adding your evidence. When the other nods, the debate has entered the data field, no longer lost in emotional dust. Commitment 7. I will favor comparison over sensationalism. When 7 comets arrive together, the value lies in placing them side by side. The small practice is to make a comparison chart. Iron tail length, recovery speed after break, dust tail curvature, and position relative to the ecliptic plane. A small chart pinned on the fridge can teach a child how to read rules better than a long essay. Commitment 8. I will leave a small promise at the end of each night. A promise is the thread linking you with yourself and with those listening to your story. The small practice is the last line in the logbook. If tomorrow the G-index rises 1 level, I will recheck tonight's tailbrake angle. Promises turn observation into sequences. Sequences turn curiosity into knowledge. 8 commitments may sound like many, but each is just a small step. When they come together, you have a lifestyle shared with the sky. I add 4 soft habits to let the rare season pass in peace. The habit of breathing. Before each observation, inhale 1 beat, exhale 1 beat. Breath is the body's slow clock, reminding you that the tail will still be there after a moment. The habit of switching off. Turn off notifications for an hour when observing, so you truly watch instead of just scrolling. The habit of yielding. When clouds roll in, accept it. Not every night is yours. Sometimes it is the night of someone in the next town. The habit of sharing. Post a slow photo, a short note, an invitation for others to observe. Communities are not born from long posts, but from steady invitations. I want to tie the commitments to very concrete American life. In the Midwest, you can invite neighbors to sit on folding chairs in front of the garage, each bringing a cup and a question. In the Southwest, dry nights are gold. You hang a paper map on the living room wall, mark the nights you saw the tail most clearly. On the East Coast, where clouds come and go quickly, commitments of 3 and 8 help you keep patience. In Alaska, where auroras may surge strongly, commitments 2 and 5 help you narrate the rhythm between the dazzling sky and the indicators on the ground. This manifesto has one last thing I want to make clear with personal opinion. All these commitments are not to make you strict. They are to keep the joy of looking up lasting longer than 1 season. Some nights you will burst with awe at a freshly broken tail. Some nights you will see only clouds. Both nights are worth remembering if you leave a small mark in your notebook. You and I will eventually forget the loudest headline of the season, but we will not forget the feeling of sitting under the porch, hearing the deep AI voice, and knowing we are responsibly loving the sky. Tonight, before turning off the lights, you can whisper the 8 commitments like a short prayer. I will begin with a question. I will anchor claims with a measure. I will respect uncertainty. I will place emotion beside mechanism. I will cross-check multiple sources. I will restate the other's strongest argument. I will favor comparison. I will promise tomorrow. Those 8 sentences are the harbor you can return to in every rare season ahead. You and I have traveled the whole journey. From the moment NASA raised its alert tempo to the quiet nights on the porch. From a severed ion tail to the ground-level indices. From dramatic hypotheses to the very ordinary compass of thinking. 7 comets and the interstellar guest did not write prophecies. They shone a light on familiar yet beautiful rules. The solar wind stretches out ionized tails, light bends dust, and statistics remind us to distinguish coincidence from cause. I see this rare season not as a test of courage, but as a festival of physics, where you and I are both amazed and calm. If tomorrow night is clear, we can still sit on folding chairs, open the occulting disk stream, and log a timestamp. If clouds are thick, we can review the notes, refine a sentence, and teach a child one more concept. Those simple acts are the bridge connecting emotion with discipline. And when the season passes, the habits remain. Opening indices like opening a rain forecast, telling stories slowly and clearly, leaving room for the sentence, I don't know yet. To me, that is the most enduring reward. If you want to continue along with this channel in this narrative rhythm, please subscribe, turn on the bell, and leave a comment. Do you lean toward a beautiful coincidence, or toward a hidden hand we do not yet fully understand? Tell me what you have seen in your sky, and which part you want the next video to dive into. Ion tails, storm calendars, or 3-eye atlas after its dark stretch near the sun. Share this episode with a friend in the US who enjoys looking up, so that one more folding chair can be set on the porch.